Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. We speak of everything, yet we hardly grasp its magnitude. Everything is the totality of existence, the stars and galaxies, time and space, energy and matter, life and mind. It is all that is, all that ever was, all that ever will be. In its embrace are the quiet dust under our feet and the shining furnaces of distant suns, the hum of a thought and the roar of a supernova. To contemplate everything at once is to stand at the shore of an infinite ocean, awed and humbled. Even our most fleeting reflection on the cosmos can send a shiver down the spine, as if some deep part of us remembers that we are a part of this grand tapestry, woven into its very fabric. On a clear night, under a vault of stars, we gaze upward and attempt to fathom our place in a vastness without obvious bounds. We see pinpoints of light scattered across a canvas of darkness, each a sun, perhaps with its own planets and stories. We feel small, yet we are connected to all of it. The iron in our blood, the calcium in our bones, the carbon in our DNA, these were forged in the hearts of ancient stars. We are children of the cosmos, built of its matter, energized by its light, and guided by our curiosity to understand it. Through science and imagination, we stretch our minds toward the edges of the universe, seeking to grasp how all of this came to be. From time immemorial, we have gazed at the heavens and spun stories about our place among the stars. Today, our tools are telescopes and equations, but the sense of wonder remains as profound as ever. In this journey, we will blend science and poetry, fact and metaphor, as we explore the cosmos on every scale. We will touch on cosmology and physics, astronomy and mathematics, philosophy and human curiosity, all the lenses through which we seek understanding. Together, let us venture to the very beginning of time and back, and to the farthest reaches of space, in pursuit of the story of everything. Our journey begins at the very beginning, at the origin of everything we know. In the primordial darkness, before a single star had ever shone, all that would become the universe was cradled in a point smaller than an atom. It is nearly impossible to imagine. A seed of unimaginable density and heat. A single point that held the potential for galaxies, for life, for every atom and every moment in time. And then, in an instant about 13.8 billion years ago, that seed exploded into growth. There was a flash of pure creation, a moment we call the Big Bang. Time and space themselves were born in that moment. What had been nowhere became everywhere. What had been nothing became everything. The newborn universe expanded with incomprehensible fury. In a tiny fraction of a second, it swelled from microscopic to cosmic scales. This extraordinary growth spurt, known as cosmic inflation, stretched space like a balloon inflating at faster than light speed. Distances between points grew by an enormous factor, smoothing out any clumps or curves. Inflation explains why the universe today is so uniform and flat on large scales. It was as if any initial wrinkles in space were ironed out by this tremendous expansion. A smooth, seething fireball emerged from that initial burst. Tiny quantum fluctuations, random little flickers of density in that early vacuum, were blown up by inflation into slight variations in the otherwise even spread of matter. These faint imprints would one day guide the formation of galaxies, but for the moment, the infant universe was a hot, dense soup of energy. As inflation settled, the energy driving it transformed into matter and light. The universe was 1 second old. In that first second, space was filled with an intense, blinding glow, radiation so hot that it would have vaporized anything, though as yet, there was nothing but fundamental particles. Matter and energy were not yet distinct. They flowed together in a plasma, a fluid of raw creation. Protons and neutrons jostled in temperatures of billions of degrees. In the minutes that followed, the entire universe itself became a nuclear reactor. These building blocks began to combine in countless tiny nuclear forges across the young cosmos. Protons fused with protons, neutrons linked with protons. By 5 minutes of cosmic time, the first atomic nuclei had formed. The simplest elements came into being: hydrogen, the lightest of all, and helium, its slightly heavier kin. A trace of lithium also appeared. In that brief early epoch of nucleosynthesis, the universe forged the basic chemical foundation it would use to build everything else. About 3/4 became hydrogen and 1/4 helium by mass, an elemental newborn universe. Still, no atoms as we know them could yet exist. The universe was far too hot for electrons to settle into orbits around nuclei. Instead, electrons careened freely through the dense plasma, scattering light incessantly. Photons, the particles of light, were trapped in a cosmic fog, bouncing from one free electron to another. Space glowed as bright as the interior of a star, but no light could travel far. The universe was opaque, a brilliant radiance suffused within a swirling, glowing mist. As seconds turned to minutes, minutes to hours, and hours to years, the young cosmos continued to swell and cool. Hundreds of thousands of years passed. Expansion took its toll on the fireball, diluting and cooling it steadily. At around 380,000 years after the Big Bang, a critical threshold was crossed. The temperature fell enough that electrons could finally be captured by nuclei. Protons clutched electrons to form hydrogen atoms. Helium nuclei gathered electrons to become helium gas. This transition is called recombination, though it was the first time such combination had occurred. With electrons now bound into atoms, the fog lifted. The once captive light was free at last. In every direction, a brilliant afterglow burst forth and raced away through space. The universe that had been opaque became transparent. That first light still surrounds us today. It has cooled to a gentle microwave glow that bathes the entire sky. The cosmic microwave background, the oldest light we can see. Back then, it was a searing, orange-white illumination everywhere. As space expanded and cooled, that light's wavelength stretched beyond red, through infrared, and into the microwave part of the spectrum we detect today. Discovered as a faint hiss in radio antennas, this afterglow is a whisper from the time the universe took its first breath as a transparent cosmos. The universe then entered a deep, dark age. With the primal light released and streaming onward, space itself went dark. There were not yet any new sources of light. The primordial gases, mostly hydrogen and helium, now drifted through expanding space like a vast, invisible fog. Gravity, the great sculptor, began to gently tug on the ever-so-slight variations in density left by inflation. Regions that were just a bit denser than average exerted a stronger pull, drawing in matter from their surroundings. Invisible threads of gravity started weaving patterns in the darkness. Over tens of millions of years, those threads pulled gas into clumps. The silent clouds grew denser and tighter until, at last, there was fire again. Perhaps 100 million years after the Big Bang, the first stars were born. Deep in massive collapsing clouds of hydrogen and helium, the pressure and heat ignited nuclear fusion. Starlight pierced the darkness. These first stars were giants, short-lived behemoths burning hot and blue, forging heavier elements in their cores as they shone. They lived for only a few million years before dying in titanic supernova explosions, seeding the surrounding space with the new elements they had cooked up: carbon, oxygen, nitrogen, iron. Ingredients that one day would be essential for planets and life. The death of each star sent enrichment into space, and out of the ashes, new generations of stars would eventually form. Their brilliant ultraviolet light also gradually burned off the primordial hydrogen fog in intergalactic space, reionizing the cosmos and allowing light to travel freely everywhere. With the birth of stars, the cosmos had begun to light up structure by structure, ending the long night of the Dark Ages. The cosmic dawn gave way to a growing day as the first stars and nascent galaxies illuminated the heavens. As stars gathered, they formed the first proto-galaxies, small galactic building blocks that later merged into larger ones. Gravity continued its tireless work on grander scales. Stars bound themselves into galaxies, and galaxies gravitated into clusters. Over hundreds of millions, and then billions of years, a vast cosmic web took shape. Galaxies pulled on one another along filaments of invisible matter, collecting into chains and sheets. Imagine a spider's web made not of silk but of galaxies, strung along invisible filaments, with enormous voids of near-empty space in between. Astronomers mapping millions of galaxies, for instance in the Sloan Digital Sky Survey, have unveiled this vast cosmic web in detail, huge filaments like the Sloan Great Wall stretching across hundreds of millions of light-years, and immense voids nearly empty of galaxies. It serves as the large-scale structure of the universe. Galaxies grouped like sparkling dew on cosmic threads, clusters at their intersections, and between them, great dark gaps where few galaxies shine. Interestingly, researchers have even drawn analogies between the cosmic web and biological systems. One experiment showed that a slime mold, when presented with simulated galaxy clusters as nutrient sources, grew tendrils that closely traced the filaments of the cosmic web, as if nature repeats patterns on vastly different scales. From a vantage point far away, the universe would look foamy or spongy, matter gathered into fibrous clusters surrounding empty cavities. And within each galaxy, countless stars swirled, orbiting their galactic centers like bees around a hive. What about the universe as a whole? Is it shaped like a sphere, a saddle, a donut, or an infinite flat expanse? As far as we can discern, space on the largest scales is remarkably flat, like an endless plane. If you set off in a straight line among the galaxies, you would not curve back around to where you started, at least not within any distance we can observe. The cosmos could extend forever, infinite in extent. It might also be finite yet unbounded, curving back on itself only on scales beyond our observational reach, rather like the surface of a balloon is finite, yet has no edge. Current measurements of cosmic geometry show no significant curvature. To the best of our knowledge, parallel beams of light travel straight and never meet. It is currently unknown whether the universe might eventually loop back in some topologically complex way, like a 3D torus. But if it does so on a scale far larger than the observable horizon. In all directions, space stretches out similarly, giving us no hint of an edge or a boundary. We are, however, limited in what we can see, not by any solid wall at the universe's edge, but by time itself. The observable universe is a sphere around us, about 46 billion light-years in radius, delineated by the distance light has been able to travel since the Big Bang. We can only see as far as the light that has had time to reach us. Beyond that horizon, light from those regions has not yet arrived, and perhaps never will. Thus, we gaze out at a bubble of the universe around us. Beyond it, the mystery continues, perhaps with more galaxies and more cosmic web stretching indefinitely, or perhaps something radically different. For now, it remains hidden, a tantalizing unknown just out of reach. The cosmic horizon is not only a physical limit, it's also a reminder of our cosmic myopia. It's like standing on the shore of a vast ocean at night. We see the dark waters meet the sky at the horizon and wonder what lies beyond. Our cosmic horizon is such a shore, and though we cannot see past it, we imagine an endless sea beyond. Even as structures formed and stars lit up, the overall expansion of space never halted. The universe kept stretching, carrying galaxies farther apart from each other. The very fabric of space is like an ever-expanding canvas, and the galaxies are like dots of paint on that canvas, drifting away as the canvas grows. The light that travels between galaxies is stretched too. As space expands, wavelengths of light elongate, shifting toward the red end of the spectrum. Thus, when we observe distant galaxies, their light is reddened, a cosmological redshift that encodes their motion through the expanding space. In the early 20th century, astronomers armed with new telescopes made a profound discovery. Nearly all galaxies beyond our local group are racing away from us, and the farther they are, the faster they recede. Edwin Hubble measured this relationship, finding that the speed of recession is proportional to distance. Today, this rate of expansion, known as the Hubble constant, is roughly 70 kilometers per second per megaparsec, meaning a galaxy about 3.3 million light-years away recedes at roughly 70 kilometers, and one twice as far at about 140 kilometers. This linear relationship, now called Hubble's law, was revolutionary evidence that the universe is expanding uniformly in all directions. It is not that we are at the center of an explosion, but rather that space itself is swelling, so every galaxy sees others moving away. Imagine raisins in a rising loaf of bread. Each raisin sees the others receding as the dough between them expands. Just so, our Milky Way and all galaxies are like raisins embedded in the expanding space of the cosmos. Yet even as Hubble and others revealed an expanding universe, other observations soon uncovered a deeper mystery in those galaxies. In the later 20th century, astronomers like Vera Rubin noticed that stars at the outskirts of spiral galaxies were orbiting their galactic centers at startling speeds, too fast to be explained by the gravity of the visible stars and gas alone. According to Newtonian physics, those outer stars should have been flung off into space, or conversely, one would need far more mass in the galaxy to hold them in their orbits. Something unseen, some additional gravitating mass, was providing the extra pull. Similarly, clusters of galaxies were found to contain far more gravity than the visible matter could supply. It was as if an invisible halo of mass surrounded clusters and individual galaxies alike. This mystery substance was dubbed dark matter. It does not shine or interact with light, making it invisible and detectable only through its gravity. But it is abundant, far more abundant than the ordinary matter we see. Roughly 85% of the matter in the universe is dark matter, about 5 times more mass than in normal atoms. It acts as the scaffolding of the cosmic web. It clumps under gravity, forming massive halos, and ordinary gas falls into those halos to form galaxies. Without dark matter's guiding hand, the universe would lack much of the structure we observe. Galaxies might not have had enough gravitational glue to coalesce as they did. We even observe gravitational lensing, light from distant objects bending around invisible mass, revealing dark matter's presence. In colliding galaxy clusters like the Bullet cluster, the normal matter, hot gas visible in X-rays, can be seen to separate from where most of the gravity is. The gravitational center follows the unseen dark matter, providing direct evidence of this hidden mass. We still do not know what dark matter is, perhaps some as yet undiscovered elementary particle that interacts only weakly with normal matter, often hypothesized as WIMPs or axions, or something more exotic like primordial black holes or a modification of gravity itself. Experiments deep underground and in particle accelerators are attempting to detect dark matter particles directly, so far without success. For now, we infer dark matter's presence by how it holds galaxies together and how it tugs on light passing by. It is the universe's invisible skeleton, a shadowy scaffolding that shaped the beautiful pattern of galaxies and clusters, all while remaining hidden from our eyes. As if dark matter were not mysterious enough, an even stranger ingredient dominates even that. For a long time, scientists assumed that the expansion of the universe, while continuing, should be slowing down over time. After all, gravity pulls all matter together. The collective gravity of galaxies, dark matter, gas and stars should gradually tug at the expansion, perhaps even causing it to reverse in the far future. But in 1998, two teams of astronomers observing distant Type Ia supernovae, exploding stars used as standard candles, made a shocking discovery. The supernovae were dimmer and farther away than expected, indicating that the expansion of the universe was not slowing at all. It was speeding up. Over the last few billion years, the galaxies have been accelerating away from each other. Some kind of force or energy inherent to space is pushing them apart. Decades earlier, Albert Einstein had introduced a cosmological constant into his equations of general relativity to allow for a static universe, not realizing the universe actually expands. When Hubble's expansion came to light, Einstein reportedly called that constant his greatest blunder. But now, the accelerating cosmos implies something like Einstein's constant truly exists after all. We call this phenomenon dark energy, a name that signifies how little we truly understand it. Dark energy appears to be a property of space itself. Every cubic centimeter of vacuum seems to carry a minuscule amount of energy that, summed over billions of light years of emptiness, dominates the universe. Today, roughly 68% of the universe's total energy content is this dark energy, with about 27% dark matter and only 5% normal matter composing the rest. It behaves almost like an anti-gravity, driving galaxies apart on large scales and overpowering the attractive force of gravity at cosmological distances. Perhaps dark energy is a fixed property of the vacuum, a realization of Einstein's cosmological constant, or perhaps it changes over time, a dynamic field dubbed quintessence. Upcoming observatories and surveys are dedicated to measuring the expansion history more precisely, in hopes of discerning the true nature of this mysterious energy. For now, dark energy remains an enigma at the heart of cosmology, a gentle but inexorable push woven into the fabric of space-time. What does an accelerating expansion mean for the future? The fate of the universe hinges on dark energy's nature. If dark energy remains constant, a steady push that continues indefinitely, then the expansion will not only continue, but accelerate forever. Galaxies that are not gravitationally bound to us will recede faster and faster, eventually zooming away at such speeds that their light can no longer reach us. In tens of billions of years, distant galaxies will disappear beyond our horizon, leaving only the gravity-bound local group of galaxies, by then likely merged into one large galaxy, visible. If we look far, we'll see darkness where once galaxies twinkled. Over extremely long timescales, the stars within our remaining galaxy, or merged Milk-Dromedar galaxy, will age and die. New stars will form more slowly as the available gas becomes sparse. Trillions of years from now, the last stars will exhaust their fuel and flicker out one by one, leaving a universe populated only by faint stellar remnants, white dwarfs cooling to black, neutron stars, and black holes. The cosmos will grow colder and darker as eons pass. Eventually, even black holes will evaporate via Hawking radiation, on timescales so vast, 100 years or more, that they defy imagination. What remains will be a thin haze of fundamental particles and energy, spread so dilute that for any given volume of space, on average, there might be essentially nothing in it. This is the Big Freeze or heat death scenario, a universe that expands forever while cooling asymptotically toward absolute zero, approaching a state of maximum entropy where no organized energy remains to do work. If an astronomer were alive in that far future of a Big Freeze, they would see a very different sky. Beyond our small gravitational neighborhood, no galaxies would be visible at all, only an endless black void punctuated by the occasional faint glow of a red dwarf or the spark of a distant supernova, becoming rarer with time. The evidence of the Big Bang itself would fade. The cosmic microwave background, which today is a cool 2.7 K glow, would be stretched to radio waves so long and weak as to be undetectable, The chemical elements would slowly transmute as protons perhaps decay over immensely long times, if proton decay is a real phenomenon. Eventually, it would be a universe of scattered particles and low-energy photons, drifting in an ever-growing silent darkness. Time would continue, but virtually nothing of interest would happen. It is a state as close to true cosmic stillness as can be. The universe would have effectively died, not with a bang, but with a long, drawn-out whimper. There are even more violent speculative possibilities. If dark energy is not constant but instead grows stronger with time, imagine a form of phantom energy, then the acceleration would steepen catastrophically in the far future. In such a scenario, the repulsive effect of dark energy could increase without bound. One could imagine the final moments of such a universe. Galaxies rush away from each other at ever-increasing speeds. Eventually, in the distant future, the expansion's pull becomes so strong that it overcomes the gravity holding galaxies together. First, galaxy clusters are pried apart. Later, the galaxies themselves begin to fly apart as their stars disperse into the expanding void. Then solar systems destabilize, planets drift away from their stars. As the end approaches, even stars and planets themselves would be torn apart, and then molecules and atoms. In the last fractions of a second, the tidal forces of expansion would become essentially infinite, shredding the very subatomic particles. This hypothetical final calamity is called the Big Rip. It would be a universe ending in a kind of ever-accelerating explosion, where every bond, gravitational, electromagnetic, even nuclear, is overcome by the expansion of space. One moment, you might have galaxies. Moments later, only individual atoms. Finally, nothing at all but a thin, featureless energy as space rips itself apart. It's a highly speculative scenario. Current data do not favor such extreme dark energy behavior, but it serves to illustrate the dramatic ways our universe's story could conclude under different rules. On the other hand, what if dark energy were to weaken over time, or even reverse sign? Or what if the universe had contained so much matter that gravity could eventually overwhelm expansion? In those cases, the expansion might slow down, stop, and ultimately reverse. Distant galaxies that are now receding would one day halt and begin to come closer again. This is the Big Crunch scenario, the opposite of the Big Bang. In a universe headed for a big crunch, observers in the far future might see the expansion first slow to a crawl. Distant galaxies that once sped away would linger at the edge of visibility. Then, gradually, they would start to approach, their light shifting from red back to blue. The cosmos would begin to shrink. Over billions of years, separated clusters of galaxies would converge. Previously unreachable galaxies would become visible again as they rush inward. The cosmic microwave background temperature, which had been dropping, would begin to rise as the universe contracts and heats up. Eventually, the night sky would no longer be dark, but aglow, first dotted with an increasing number of bright galaxies coming together, then suffused with the glow of a background fire as intergalactic gas is compressed and reheated. In the final epoch, the entire sky might blaze like the surface of a star, white hot, as galaxies merge into a single, incandescent mass. Finally, all matter and energy would crash together in an ultra-dense state, perhaps a mirror image of the Big Bang. Some have imagined that such a collapse could bounce, an implosion leading to a new explosion, a Big Bang after the Big Crunch, giving birth to a new universe. This Big Bounce idea suggests a cyclic cosmos without beginning or end, eternally reborn. However, given what we observe, particularly the presence of dark energy, a Big Crunch seems very unlikely for our universe. The balance of evidence indicates that we are headed toward eternal expansion, either the Big Freeze or Big Rip, with Big Freeze considered far more plausible under current data. Nevertheless, thinking about these scenarios reminds us that our universe's story might have multiple chapters, and perhaps even an epilogue beyond our own cosmos. As we ponder the fate and origin of our universe, we naturally wonder, is our universe the only one, Or is it just one bubble in a vast, frothing sea of universes? Modern theories in cosmology and physics have opened the door to the idea of a multiverse, the possibility that our universe is not alone, but part of a far larger system of universes. The existence of dark energy and the precise balance of physical constants in our universe have led some to wonder if our cosmos is just one of many, its properties one random draw among myriad universes. In a multiverse, what we call fine-tuned constants of nature, like the strength of gravity or the charge of the electron, might vary from one universe to another. We find ourselves in one that permits galaxies and life simply because those that don't would be sterile and uninhabited, with no observers to notice them. One compelling multiverse idea arises from the theory of eternal inflation, a variant of the inflationary scenario we discussed earlier. In eternal inflation, the rapid expansion of space didn't end everywhere at once. While inflation stopped in our region, allowing particles and galaxies to form, other regions of space might still be inflating, or might have ended their inflation at different times, each giving rise to its own bubble universe. Our universe, then, would be one such bubble among countless others, expanding within a larger inflating space-time. Each bubble could have its own distinct laws or constants. Some might be barren, with no matter or with physics hostile to complexity. Others might be roughly similar to ours. Perhaps others are wildly different with more dimensions or different fundamental forces. We cannot directly see these other bubble universes because they would lie beyond our cosmic horizon and indeed beyond any space-time connection with us. But they are a natural extrapolation of inflation theory. These other universes could be as real as our own, each constituting its own reality bubble. The multiverse concept comes in different flavors. The Level 1 multiverse essentially says that if space is infinite and uniformly filled with matter, then far beyond our observable horizon, there could be regions identical to ours, or slightly different or vastly different, simply by random chance arrangements of matter. In an infinite universe, every possible configuration of particles, every possible history, would occur somewhere. Our observable universe would be just one patch of an infinitely vast quilt. The Level 2 multiverse corresponds to the eternal inflation scenario, bubble universes. Each bubble might have different physical constants or particle types, because the process of symmetry breaking in physics could end up differently in each one. One bubble might have a stronger electromagnetic force. Another might have a neutron a bit heavier, preventing stars from working. We find ourselves in a bubble that is congenial to complexity because only such bubbles can produce observers. Another intriguing idea is the Level 3 multiverse, which arises from quantum mechanics, the many worlds interpretation. In quantum theory, every event that has multiple possible outcomes, like a particle decaying or not decaying, is sometimes thought of as splitting reality into multiple branches. According to this interpretation, all possible outcomes actually occur, each in its own branch of the wave function of the universe. So in one quantum branch, universe, the cat is alive. In another, it is dead, to invoke the famous Schrödinger's cat thought experiment. These parallel universes are usually thought to be non-communicating, existing in a superposed mathematical state, rather than separate inflating bubbles. But some argue they are just as real as our own. In effect, this would mean that with every quantum event, the universe, at least at the level of quantum information, splits into multiple histories, creating an ever-branching tree of parallel realities. If true, the number of universes would be mind-bogglingly large and constantly increasing. There is even a conjectured Level 4 multiverse, the ultimate ensemble, which posits that all universes that can be described by consistent mathematical structures exist in some sense. In this view, mathematics and reality are one and the same. Any self-consistent set of physical laws, any mathematical model, corresponds to an actual universe somewhere. This is a philosophical speculation more than a scientific theory, but it underscores how far the multiverse idea can be taken. So, could it be that what we call everything, our observable cosmos, is but a drop in a much grander ocean of existence? It's possible. At present, the multiverse remains a theoretical idea. We have no direct evidence of other universes, and some argue we never could, by definition. Yet the concept finds footing in serious science because it can arise naturally from models like inflation, and because it offers answers to questions like why our universe has the properties it does. They might be random picks from a larger distribution. If the multiverse is real, then the totality of existence is even grander than the universe we've been discussing. It means there could be countless other Big Bangs, countless other expansions, perhaps countless other versions of you and me, or perhaps realities utterly without analogy to anything we know. It is a speculative, almost metaphysical extension of our theories, one that reminds us that as vast as the universe is, there could be more, much more, beyond it. No matter how many universes exist, we know that we can only directly explore our own, and it has plenty of mystery to keep us occupied. One such mystery is deeply connected to our everyday experience, the nature of time. Time flows ever forward, carrying us from moment to moment. We remember the past and anticipate the future, but we never experience events in reverse. This one-way direction of time, from past to future, is called the arrow of time. Why does time have an arrow? The answer, as far as physics can tell, lies in entropy. Entropy is a measure of disorder or randomness. The second law of thermodynamics states that in an isolated system, entropy tends to increase or, at best, stay the same. It never decreases spontaneously. This law gives a direction to processes. Things go from ordered to disordered, not the other way around. An egg breaks and scrambles, but a scrambled egg does not unbreak itself into a whole egg. A drop of ink disperses in water, but the ink won't gather back into a concentrated drop on its own. These processes are not forbidden by any fundamental microscopic law. Newton's and Schrödinger's equations work the same forward and backward in time, but they are overwhelmingly unlikely to happen in reverse, because that would require a decrease in entropy. The arrow of time in our universe is fundamentally linked to the initial conditions of the cosmos. The universe began in an extraordinarily low entropy state. This might sound strange because the early universe was a hot, dense plasma which seems very disordered, but in fact, it was extremely uniform and simple, free of complex structures, making its entropy lower than it could have been. It's as if all the matter and energy were evenly spread out and gravitationally unclustered, a very ordered configuration compared to what could be. Because the universe started with such low entropy, there was essentially nowhere to go but toward higher entropy. As the universe expanded and cooled, entropy increased, gradients smoothed out, structures formed even as overall disorder grew. For example, the formation of stars and galaxies increases local order, but overall entropy still rises due to the production of lots of waste heat and the gravitational settling that releases energy. The arrow of time is a manifestation of this rise of entropy. We perceive time flowing forward because that is the direction of increasing entropy. If you were to film a glass shattering and play it backwards, you'd see entropy decreasing and immediately intuit that time is reversed in the film. In the real universe, we do not see such things. One might ask, why was the entropy of the early universe so low to begin with? This remains one of the deep, unanswered questions in cosmology. Some suggest it might be a boundary condition of our universe, perhaps set by a prior state or by the laws of quantum gravity. Others propose that if there are multiple universes or cycles, we naturally find ourselves in one that started in a low entropy state, because only such a universe can develop the complexity needed for observers. Regardless, that low entropy beginning is what allowed an arrow of time to emerge. From it flowed the entire history of structure and complexity. Stars shine, increasing entropy by radiating heat. Life grows and metabolizes, increasing entropy in surroundings even as it creates local order. And eventually stars die and things run down. If we project trillions upon trillions of years forward, in the heat-death scenario, entropy will near a maximum. The arrow of time will effectively fade, not because time has reversed, but because almost nothing changes anymore. There are no organized processes left to distinguish a forward direction. In the far, far future of a big freeze, the universe might reach a state of near equilibrium where, without gradients or differences, the concept of before and after loses much of its meaning. Time and entropy tie together the grand cosmic and the intimate personal. The increase of entropy sets the thermodynamic arrow that makes memory possible. We remember lower entropy past states. It is why we grow older and not younger. It's the reason we can't unmix cream from coffee or unburn a piece of paper. It's fascinating that this everyday irreversibility is rooted in the initial conditions of the entire universe. We've journeyed from the enormous clusters of galaxies to the minute atoms and particles, but we haven't yet delved into the truly fundamental fabric underlying reality, the quantum realm. On the smallest scales, the world behaves in ways that defy our classical intuitions. In the quantum realm, particles are also waves, and everything is described by a fuzzy haze of probabilities rather than definite certainties. Take an electron. In an atom or in transit, it doesn't have a single precise location. Rather, it exists as a cloud of probability, a smeared-out wave of potential positions. Only when we interact with it, measure it, does the electron seem to choose a location or state. This is the bizarre phenomenon of wave function collapse, in interpretations where collapse is a thing. Before observation, Schrödinger's cat is both alive and dead in a quantum sense. Before measurement, the electron has many possible positions. For example, if we shoot electrons at a screen through two narrow slits, something astonishing happens. The electrons, one by one, form an interference pattern on the detection screen, alternating bands as if they were waves that passed through both slits and interfered with themselves. This happens even if we fire them one at a time. It's as though each electron goes through both slits as a spread-out wave. However, if we set up a detector to observe which slit the electron actually goes through, trying to catch it in the act and force it to be a particle going through one path, the interference pattern disappears. Now the electrons behave like little bullets, going through one slit or the other, and no interference fringes form, just two piles behind the slits. The mere act of observation changes the outcome at the quantum level. It's as if nature allows the electron to explore many possibilities, wave behavior, until we insist on knowing which one happened, at which point nature chooses and the wave of possibility collapses into a single result. Empty space itself is not truly empty in the quantum sense. Even in a perfect vacuum, quantum fields are continuously fluctuating. Particle-antiparticle pairs momentarily pop into existence and then annihilate so quickly and so spontaneously that we can barely infer their presence. They leave subtle effects on energy levels and forces. These quantum fluctuations are not just theoretical quirks, they had cosmic consequences. During inflation, those tiny fluctuations in density and energy were stretched out to macroscopic scales. Regions that were ever so slightly more dense or less dense than others became the seeds for all large-scale structure. The spots in the cosmic microwave background that are a bit warmer or cooler, denser or less dense, trace back to these quantum wiggles. It is a breathtaking linkage. The reason galaxies exist where they do is partly because of random subatomic jitter in the universe's earliest moments. The entire cosmic web is essentially amplified quantum noise. Quantum physics underpins nearly everything in our daily experience, even though we don't notice its strangeness on large scales. The atoms in our bodies are held together by electron wave functions and quantum bonds. The sun shines because quantum tunneling allows protons to overcome their electrostatic repulsion and fuse into helium. Without quantum tunneling, the sun's core wouldn't ignite as easily. Computers and modern technology rely on quantum mechanics, semiconductors, lasers. In a sense, the solidity of a rock, the behavior of a chemical reaction, the colors of the rainbow, all trace back to quantum rules. We live in a quantum universe, though its oddness becomes apparent only when we look at small scales or specific conditions. There is also the deep mystery of quantum measurement and reality. Does the wave function collapse when observed? Does the universe split into branches for each outcome? The many worlds idea. No one knows for sure which interpretation of quantum mechanics is correct, or if there's a deeper theory that will resolve these questions. What we do know is that quantum mechanics is astoundingly successful in predicting outcomes. It has been tested to high precision. Reality, at its foundation, is governed by probability waves and uncertainty. It's almost as if nature, at a fundamental level, decides events by a kind of controlled randomness within strict statistical rules. Our voyage has taken us from the beginning of time to the structure of space, from the largest assemblies of galaxies to the subatomic flickers of the vacuum. Along the way, we encountered phenomena that are poetic in their grandeur and scientific in their detail. An afterglow from creation itself still shining to us, invisible matter holding galaxies in its gravitational embrace, a mysterious energy pulling the cosmos apart, and quantum whispers setting the stage for galaxies. Let's return for a moment to that ancient light we freed at recombination, the cosmic microwave background, CMB. After traveling for 13.8 billion years, it reaches Earth as a faint, cold glow in all directions, a few photons per cubic centimeter. In 1965, two engineers, Arno Penzias and Robert Wilson, were using a big horn antenna in New Jersey, trying to eliminate all sources of noise from their radio measurements. They kept encountering a persistent hiss, uniform across the sky, day and night. At first, they thought it might be due to urban interference, or pigeon droppings in their antenna, or instrument malfunction. But none of those explained it. Meanwhile, a group of physicists at Princeton, Dicker, Peebles, et al., had been looking for exactly such a signal. The predicted relic radiation from the hot early universe, which years earlier, scientists like George Gamow had calculated should by now be just a few degrees above absolute zero. Penzias and Wilson had stumbled upon the very signal that those theorists were seeking. It was soon confirmed that this microwave hiss came from all directions uniformly and had a blackbody spectrum of about 2.7 Kelvin, just what the Big Bang model predicted. The cosmic microwave background was the long-predicted afterglow from the hot young universe, now cooled to a whisper. When we map the CMB across the sky, as satellites like COBE in 1989, WMAP in the 2000s, and Planck in 2013 have done with increasing precision, we find it is almost the same in every direction, extremely uniform to about 1 part in 100,000. It's as if the entire sky were painted with one color of incredible smoothness, with only the faintest speckles. Those speckles, the tiny temperature anisotropies, carry a wealth of information. They are the imprints of the primordial sound waves and density ripples in the early universe. The pattern of spots tells us the universe's age, composition, and geometry. By carefully analyzing the CMB, scientists have confirmed the age of the universe, how 13.8 billion years, determined that space is flat to within a tiny margin of error, and measured the ratios of normal matter, dark matter, and dark energy that we mentioned. The CMB is like a baby picture of the universe, taken when it was only 380,000 years old. In that baby picture, we can already see the slight non-uniformities that eventually grew into clusters of galaxies. It's astonishing that we can observe this. When you tune an old television between channels and see static, a small fraction of that static is actually CMB photons. literally relics from the Big Bang hitting your TV's antenna. The CMB also provides evidence that ties together many threads of our story. It confirms the Big Bang. A static universe would not have such a background. It supports inflation. The uniformity and specific patterns match inflationary predictions. And it informs the dark matter models. The CMB pattern is sensitive to the amount of invisible mass. It is a Rosetta Stone for cosmology, decoded through careful, rigorous science. And yet, when one simply gazes at the visualizations of the CMB, with its gentle swirls of red and blue, indicating tiny temperature fluctuations, one can't help but feel a sense of wonder. This mottled oval image, often shown in textbooks and documentaries, is the imprint of the primordial cosmos on the sky, the oldest light we will ever see, a light that has traveled for almost the entire history of the universe to reach us. Within this vast cosmic unfolding, on at least one small planet, the expansion and cooling of the universe eventually led to something new: life and consciousness. The atoms forged in stars and scattered by supernovae became the raw material for new star systems. About 4.6 billion years ago, one particular cloud of gas and dust, already enriched by previous generations of stars, collapsed to form our Sun and its family of planets. The third planet from this sun had the right conditions for a remarkable chemistry. In its early oceans and coastal environments, a rich molecular broth swirled. On this young Earth, a complex chemistry brewed in warm ponds, in tidal pools, and around underwater hydrothermal vents. Complex molecules formed in the warm, wet cradles, perhaps sparked by lightning in the atmosphere or by geothermal energy in the crust. Perhaps in sunlit shallow pools, left to evaporate on volcanic shores, or in the mineral-rich hot springs on the ocean floor. Simple chemistry crossed the threshold to self-replication. At some point, simple self-copying molecules emerged. This was the origin of life, around 4 billion years ago. From those humble beginnings of primitive microbes, life evolved in complexity and diversity, shaped by mutation, competition, and time. Tiny cells coalesced into more complex cells, which eventually formed multicellular colonies. By around 540 million years ago, the Cambrian explosion filled the seas with an astonishing variety of creatures. Life took hold on land. Plants and fungi colonized the continents, followed by insects and amphibians, then reptiles and dinosaurs. Each living organism was, and is, a little chemical machine, drawing energy from the environment to maintain its internal order, a local reversal of entropy paid for by increasing entropy in its surroundings. In this way, life is a kind of cosmic rebellion against the trend toward disorder, though only a temporary and localized one. Through life, the universe explored an entirely new realm of complexity. After dinosaurs were wiped out 66 million years ago by an asteroid and other factors, mammals rose to prominence. Some primates in Africa, a few million years ago, left the trees for the savanna. They grew bipedal and clever. They made tools and learned to cooperate in groups. By about 300,000 years ago, anatomically modern humans had appeared. With the emergence of Homo sapiens, the universe began to be aware of itself in an unprecedented way. We gazed at the stars with curiosity and imagination. Over thousands of years, we developed language, culture, mythologies about the cosmos. We harnessed fire, energy for entropy consumption. We built shelters. We eventually tilled fields and founded cities. We looked up and saw patterns in the sky, crafting constellations and calendars. Human curiosity pushed us to ask not just how to survive, but why we are here, what the stars are, what the sun is, and how it all began. Fast forward to the modern era. In just the past few centuries, we have, through the scientific method, unraveled many cosmic mysteries. We discovered that those points of light in the night sky are other suns, and some of those suns host planets of their own. We've confirmed thousands of exoplanets and infer that the galaxy holds billions more. We found that our sun is just one star among hundreds of billions in the spiral galaxy we call the Milky Way, and that our galaxy is just one of trillions in the observable universe. We've begun to understand the forces and particles that govern nature. We've peered back in time with powerful telescopes to see galaxies in their infancy, and we've peered into the atom to unlock the secrets of quantum physics. Life, at least here, evolved to consciousness that can contemplate the universe. That is a profoundly poetic fact. We are made of dead stars, and those very ashes have somehow become alive and able to wonder about their origins. The universe spent billions of years evolving us, and through our eyes, it now sees itself. We are a way for the cosmos to know itself, Carl Sagan famously said, encapsulating this truth. Our self-awareness makes the universe not only a physical phenomenon, but also an experience. Through our literature, art, and science, the cosmos has gained the ability to reflect upon itself, to study its own laws, to admire its own beauty. Are we alone in this astounding capability? Perhaps not. The universe is so vast that it seems improbable that Earth would be the only cradle of life. Perhaps in some warm pond on an exoplanet under a distant sun, chemistry has given rise to biology. Perhaps on a moon orbiting a gas giant, beneath an icy crust, alien microbes flourish near thermal vents. Maybe on some planet in the habitable zone of another galaxy, intelligent creatures build their own tools and look up at their sky with questions. As of now, we don't have evidence of life beyond Earth, but the possibility stirs our imagination. Whether life is common or exceedingly rare, the fact remains that life here has transformed a part of the cosmos into something self-aware. And so here we find ourselves, clever, self-aware creatures built of cosmic dust, living on a minor planet, orbiting an ordinary star in a typical galaxy, yet able to contemplate the entirety of existence. Our physical insignificance is undeniable. We are infinitesimal compared to the breadth of the cosmos. Our entire world is just a tiny mote of dust in a cosmic ocean, a pale blue dot adrift among countless stars. But our ability to understand and appreciate the cosmos gives us a significance of a different kind. We might be rare, perhaps the only intelligent beings for parsecs around, or maybe one of only a few in our galaxy. Maybe life teems in the universe, or maybe it is exceedingly scarce. Either way, in our corner of space and time, we are the only known eyes and minds observing the grand cosmic drama. Through us, the universe has become aware of itself. Through our scientific instruments, the universe maps its own structure. Through our poetry and art, the universe speaks of its own majesty. There is something profoundly meaningful about this, even if one views it in a purely secular, scientific way. The cosmos has given rise to beings who can know the cosmos. We have inherited the fiery hearts of ancient stars in the iron of our blood, the calcium of exploded supernovae in our bones, and the carbon and oxygen from countless stellar furnaces in every organic molecule of our bodies. We are literally children of the stars, made of stardust. And those children can now, like grown progeny, look back and study their parents, the stars, and grandparents, the galaxies, the Big Bang. This unity of origins gives us a connection to everything. We are not separate from the universe. We are portions of it, inextricably linked. The laws of physics that formed a galaxy also form the neurons in our brain that fire when we gaze at a galaxy. With knowledge, however, comes the humbling realization of how much we don't know. Our journey through cosmology answers many questions, but raises others. Why is there something rather than nothing? Did time begin with the Big Bang, or is there a multiverse with different realms beyond ours? What is the true nature of space and time on the smallest scales? Are they quantized into discrete bits, as some theories like quantum gravity suggest? We don't yet have a fully unified theory of quantum mechanics and gravity. Thus, the exact first moments of the Big Bang, the Planck time, and what happened before inflation remain mysterious. We still do not know what dark matter is, despite it making up most of the matter in the universe. We still do not know why an early hyperinflation happened, or if it's even the final answer to the early universe's smoothness and flatness. We aren't sure if dark energy is truly constant or has subtle variations, and the nature of dark energy, why vacuum has the energy it does, is deeply perplexing. In fact, theoretical physics calculations of vacuum energy overshoot observations by an outrageous factor, a major puzzle. We do not know if life is a common cosmic phenomenon or an extremely lucky fluke confined to Earth. We have not yet detected signals from other civilizations, though projects like SETI are listening. We do not know the fate of humanity, whether we will spread to the stars or remain bound to our lovely, pale blue dot. In short, we still float on a sea of mystery, with islands of knowledge gained so far. Standing at this precipice of knowledge and mystery, one cannot help but feel a profound awe. The universe is ancient and vast beyond comprehension, yet here we are, small creatures with curious minds, capable of tracing its story from the primal fireball to the present, and even forecasting its possible futures. That story, from the simplicity of the early fireball to the complexity of a living world, is both humbling and inspiring. The cosmos is breathtaking, not just in scale, but in the way it has produced patterns and coherences. The periodic table of elements forged in stars, the spiral patterns of galaxies, the double helix patterns of DNA that allowed creatures like us to emerge. There is a deep harmony in how the same physical laws apply across all scales. The nuclear reactions blazing in the core of a distant star obey the same physics as the glow of your reading lamp. The gravity that makes a planet orbit the sun is the same gravity that makes galaxies dance around one another in clusters. Mathematics, abstract patterns of logic, proves to be an incredibly effective language to describe these laws, suggesting a wondrous connection between the human mind and the workings of the universe. It's as if the universe has a hidden symmetry or order that we can glimpse through mathematics and science. Our journey of understanding is far from over. Each new discovery in astronomy or physics tends to open new questions. When we discovered the expansion of the universe, we were led to ask about the beginning, Big Bang, and the ultimate fate. When we found the cosmic microwave background, we were led to the idea of inflation. When we observed unexpected galaxy rotations, we hypothesized dark matter. When we measured distant supernovae, we stumbled upon dark energy. Every time we peel back a layer of reality, there is another layer waiting, sometimes with stranger questions. This is the beauty of science and exploration, a continuous unfolding story, each chapter building on the last, but the book seemingly without end. Picture the cosmic timeline as a grand narrative, a story that begins with nearly featureless energy and evolves into intricate worlds and beings. It's a story that spans 13.8 billion years and perhaps will span trillions more. To grasp our place in this timeline, imagine compressing the entire history of the universe into a single calendar year. The Big Bang happens at the stroke of midnight on January 1st. By early February, the first stars ignite. By mid-March, galaxies are forming. The Milky Way might form around May. Our Sun and Earth appear roughly in early September on this cosmic calendar. Life arises on Earth by late September. Complex multicellular life proliferates in November. Dinosaurs roam the Earth on December 25th, Christmas Day, and go extinct on December 30th. Modern humans emerge only in the final hour of New Year's Eve, and all of recorded human history flashes by in the last seconds before midnight. In those final seconds, we develop agriculture, build the pyramids, invent the telescope, land on the moon, and contemplate the Big Bang. When the clock strikes midnight to herald a new cosmic year, Perhaps that represents some distant future state we've yet to comprehend. This cosmic calendar shows just how young we are. Human civilization is an eye blink in cosmic time, and even the Earth is a relatively late chapter in the story. We arrived at the tail end of the year, so to speak, but armed with curiosity and intellect, we busied ourselves in those last seconds learning about all that came in the months before us. Now we, ephemeral yet mindful, look to the future. We wonder what's next for the universe and what's next for us. Barring extraordinary intervention, the universe will continue to expand and evolve according to the physical processes we have discussed. As for humanity, we too are subject to cosmic forces, but have some say in our destiny if we are wise. We may spread to other planets, carrying our legacy of curiosity with us beyond Earth, ensuring that life and consciousness have a longer future than our single planet's fate. We may find ways to harness new energy sources or manipulate space-time, ideas once in the realm of science fiction, but who knows what knowledge awaits in the coming millennia. Or we may struggle and someday perish, becoming a brief spark that faded out. But even if our particular lineage ends, perhaps other intelligences elsewhere will carry on, or new intelligences might evolve from what we leave behind, intelligent machines, or new species. The desire to know and to wonder might itself be as resilient as life. From the standpoint of the universe, meaning is not something handed down from the stars. It is something we create. We infuse the cosmos with meaning by contemplating it. A galaxy 100 million light-years away has no idea of its grandeur. But we know, and in knowing and seeing beauty in it, we give it meaning, at least to us. In a way, the cold equations of physics blossomed into the warmth of human experience and inquiry. The universe is often described as a cold, uncaring place, and physically it is vast and mostly inhospitable. But through us, it cares about itself, in the sense that we care and we are part of the universe. This connection may be philosophically subtle, but it is emotionally powerful. Our exploration is ongoing. Even now, new telescopes like the James Webb Space Telescope peer into the distant past, seeing galaxies forming just a few 100 million years after the Big Bang, giving us new data points in the cosmic saga. Particle accelerators, like the Large Hadron Collider, probe higher energies, trying to recreate conditions just after the Big Bang, searching for clues of new physics. Perhaps particles that could explain dark matter or hints of extra dimensions. Experiments in deep mines attempt to catch a glimpse of dark matter particles zipping through Earth. Space probes explore planets and moons, looking for signs of past or present life beyond Earth. Mars's ancient riverbeds, the subsurface ocean of Europa, the methane seas of Titan. We are, in a sense, turning over every stone we can in this universe to piece together the puzzle of reality. Standing on the precipice of all this knowledge and mystery, we feel both incredibly small and incredibly enriched. The night sky no longer just offers twinkling points of light. It is a time machine, showing us distant galaxies as they were eons ago and connecting us to the moment of creation. The ground beneath us is not just dirt, it's ancient cosmic debris, a mix of elements made in star cores, arranged by geological and evolutionary processes into our immediate environment. We, the curious specks of the universe, will keep lighting candles in the cosmic dark, striving to illuminate more of that everything, even as it continually surprises us. The quest goes on, and the wonder deepens. To be alive as a human at this moment, to have consciousness, to have the accumulated knowledge of generations at our fingertips, and the ability to extend that knowledge, is a precious, fleeting gift. Through our minds, the universe has awakened to a sense of itself, however partial. We have the privilege of witnessing this vast tapestry and the responsibility of carrying that knowledge forward. In the end, the story of the universe is not just a tale of matter and energy moving heedlessly. It is also a human story, a story of awareness and curiosity finding a foothold in a vast cosmos. We began this journey meditating on the concept of everything. Now, At journey's end, we realize that perhaps we have only scratched the surface of everything. We close with more questions than we started, but also with a deeper reverence for existence. We sense that the strangeness and wonder of the universe will never end, no matter how much we discover. As long as there are beings curious enough to look up and ask questions, the cosmos will continue to inspire. In its darkness and its light, its simplicity and its complexity, its silence and its stories, the universe offers an endless well of awe. It is a beauty we could pursue forever and never exhaust, or without end. In the beginning, there was darkness, a vast and silent expanse of cold gas and dust adrift in the galactic night. For endless ages, nothing disturbed the quiet. The particles of ancient stars lay sparsely scattered, remnants of long-dead suns. Yet in that silence lived the potential for worlds and light. A gentle stirring began, perhaps the distant reverberation of a supernova's death cry, or the subtle pull of gravity drawing denser clumps together. The clouds started to swirl ever so slightly, an imperceptible dance born in stillness. Slowly, gravity tightened its grip. What was diffuse began to gather, whispering chaos into motion. At first, the movements were ponderous and slight, a drift inward here, a coalescing knot of dust there. But momentum grew. The great cloud, once tranquil and diffuse, began to collapse into itself. As it fell inward, it spun faster and faster, like an ice skater pulling in her arms. What had been a shapeless haze started to flatten into a broad disk, a whirling pancake of cosmic dust encircling an increasingly dense center. In that center, compression bred heat. Atoms pressed against atoms as the material piled in, and a hot, dense core formed, the seed of a star. Deeper and deeper, the young protostar collapsed under its own weight, temperature rising with each passing moment. The very nature of matter was changing. Gas became plasma, and hydrogen atoms, the simplest building blocks, were slammed together in an immense cosmic forge. Until at last, under crushing pressure and heat, hydrogen nuclei began to fuse into helium. In a sudden, radiant ignition, the protostar became a star. The darkness was broken by a newborn light. The sun had ignited at the heart of the collapsing cloud, and the solar system's story truly began. For the first time, our infant sun sent forth light and heat, a beacon in the void. It was not yet as steady as the elder star we know today. It burned with a ferocious, youthful energy, a T-Tauri sun throwing off violent winds. Those early solar winds blasted outward, sweeping the inner regions of the disk clear of the lightest gases and shaping the environment in which future planets would form. The new star's heartbeat, nuclear fusion in its core, created a magnetic field and an outward pressure that declared a new order in this once unremarkable patch of space. The sun's gravity now dominated, and all things would orbit around this central fire. But in those first moments after ignition, the sun was like a crying infant, brilliant, uncontained, and volatile. It sent a flood of particles and radiation washing over the surrounding disk. Yet despite this turbulent beginning, within the circling disk of gas and dust, smaller stories were about to unfold. Amid the sun's luminous new voice, the remaining material, the leftovers of starbirth, was not idle. It too continued to move and gather, heralding the emergence of new worlds. In the golden light of the young sun, countless dust grains began to stick together, first by the gentle static of their collisions, and then by gravity's growing pull. This was the dawn of the planets, formation of the solar system. Encircling the sun was a vast rotating disk of debris, glowing gas and fine dust lit by the infant star's fire. Within this protoplanetary disk, chaos reigned and creation beckoned. tiny motes of dust, no larger than powder, swirled in eddies and currents created by the disk's rotation. They collided softly, clumping into larger grains. Electrostatic forces, like a child's hair lifting toward a balloon, helped these particles adhere at first. Over thousands of years, grains became pebbles. Pebbles merged into rocks. In the dance around the sun, these rocks gathered into boulders and then into bigger chunks still. As the disk turned and thinned, regions of density emerged, pockets where material crowded together. In those regions, the clumps grew swiftly, their gravity pulling in more and more fragments as they cleared their paths. In a multitude of places, these growing bodies, planetesimals, were taking shape, the embryos of planets. They swept up dust in their vicinity like magnets. When they struck one another, sometimes they shattered in violent explosions, but more often they merged, becoming larger each time. The early solar system was a place of constant collisions, a shooting gallery of rock and ice. Every impact released energy, heating the young bodies and melting them inside if they were large enough, allowing heavy elements to sink inward and form cores, while lighter materials floated toward their surfaces. Closer to the nascent sun, only materials that could withstand fierce heat, metals and silicates, survived. Out of those solid ingredients, the inner planets were born. Farther out, beyond a certain distance, the sun's warmth waned and ices could remain solid. In those colder reaches, giants would emerge, capturing not just rock and metal, but also vast amounts of ice and gas. The disk was like a great plain of opportunity, with the sun's heat dividing it into realms. An inner realm of rock and iron, an outer realm of ice and gas. As time flowed on, dozens of protoplanets coalesced in the inner solar system. We can imagine them as a swarm of moon-sized to Mars-sized bodies circling the sun, each on its own path. They tugged at each other in passing, sometimes gently reshaping orbits, sometimes sending a neighbor careening into a new trajectory. Eventually, some paths crossed catastrophically. Two growing planet embryos might collide at tens of thousands of kilometers per hour, a titanic crash that could melt rock and strip atmospheres in an instant. These were the cosmic birthing pains. Out of violence came larger, more stable worlds. Each collision meant fewer bodies, but bigger ones. Gradually, the inner solar system's population winnowed down to 4 dominant survivors, the terrestrial planets, each bearing the scars of that tumultuous time in their craters and metal-rich cores. Meanwhile, further out, gravity was weaving even grander tapestries. In the cooler, more voluminous outer disk, a handful of colossal seeds were gathering mass at a relentless pace. Cores perhaps 10 times heavier than Earth aggregated, and once these cores were hefty enough, their gravity began to draw in the surrounding hydrogen and helium gas that permeated the disk. These future giants quickly bloated into immense spheres of gas around solid centers. Jupiter, the firstborn of the giants, might have been an early mover, a gluttonous core that vacuumed up gas and grew to monstrous scale. Not far behind, Saturn swelled into a second lord of the outer system. Uranus and Neptune were later to the feast, capturing what gas remained in their more distant orbits and thus turning out smaller, but still becoming kings of the far cold region. Yet the giants did not form in peace either. They too felt the push and pull of gravity's caprice. Jupiter especially may not have been content to stay in its lane. Some scientists imagine a time when Jupiter wandered inward toward the sun after it formed, like a restless titan lumbering through a crowded room, gravitationally scattering the smaller bodies in its path. In this scenario, Saturn's growth eventually pulled Jupiter back, their mutual gravities interacting in a complex dance that caused Jupiter to tack and migrate outward again. In its travels, Jupiter reshaped the layout of the young solar system dramatically. It swept some regions clean of would-be planets, robbed material from the inner disk, stunting the growth of Mars, which would end up much smaller than Earth, and hurled countless leftover planetesimals either into the sun out toward the distant Oort cloud, or inward to pummel the forming inner planets with a rain of impacts. Throughout this chaotic youth, impacts were unimaginably frequent. We call one period in particular the Late Heavy Bombardment, a time when the last leftovers of planet formation barraged the newly formed worlds. Every crater on Mercury, the Moon, and Mars is a memory of that era of incessant collision. Earth, too, was struck repeatedly, though wind and water have since erased most of those primordial scars. In those violent early days, a wandering rock the size of a mountain could obliterate a budding ocean or strip away a nascent atmosphere. And yet, paradoxically, some of these impacts may have also delivered vital ingredients, like water and carbon-rich compounds, to the inner planets, seeding the potential for future life. In the midst of this drama, our fledgling solar system gradually settled into a more ordered state. What had begun as a thick soup of dust and gas became a relatively flat disk with discrete, clear lanes, each dominated by a planet. The sun's once raging winds calmed, blowing away much of the remaining nebular gas into interstellar space. The major planets had largely finished growing. Now they moved in defined paths, locked in by the sun's gravity and each other's subtle tugs. The era of formation was giving way to an era of stability. The solar system was now a family of a star and its planets, orbiting in a majestic balance. Even so, some remnants of creation persisted, many minor bodies that never coalesced into planets. Between Mars and Jupiter, a band of rubble remained. The asteroid belt, composed of pieces of rock and metal that Jupiter's gravity had prevented from assembling into a world. And farther out, beyond Neptune, innumerable icy fragments lingered in the dark, forming a distant halo and belt of frozen relics. These leftovers would be the source of comets and meteorites for eons to come, cosmic messengers carrying clues of our origin. Thus, from the initial collapse of a dark cloud to a bright new star surrounded by planets, the solar system emerged. It is a story of violence and grace, destruction and creation hand in hand. Each world that survived carries the memory of those times, in craters, in tilted axes, in moons that likely formed from shattering impacts. The stage was now set. The sun burned steadily at the center, and around it revolved a diverse cast of planets, great and small, each unique, yet bound by a common origin, each awaiting its own story in the unfolding cosmic drama. The sun. At the center of it all blazes the sun, a gentle tyrant, a brilliant guardian, the life-giver and occasionally life-taker. The sun is our star, a true stellar furnace that has burned for billions of years and will burn billions more. In its core, the primordial fire kindled during its birth continues to rage quietly and ceaselessly. There, at temperatures of millions of degrees and under crushing pressure, hydrogen atoms fuse into helium, releasing energy that slowly percolates outward. What began as the faintest glimmer in the dark has become a roaring engine of nuclear fusion. The sun's core is like a heartbeat for the entire solar system. Its steady output of energy is the pulse that warms the planets and defines the rhythms of day and night, season and year. From its bright face, the photosphere, streams the light that illuminates all our days. Photons born in the sun's core may take tens of thousands of years to fight their way out from the dense interior, bouncing from particle to particle in a chaotic journey, only to burst free at last and zip across space in 8 minutes to reach Earth. This sunlight is the visible sign of the sun's constancy. Every sunrise testifies that the sun is still there, still pouring out the energy that keeps Earth's oceans liquid and its forests green. To us, the sun appears eternal, unchanging, but it too lives a life cycle on a scale far beyond human lifetimes. For now, it is a stable middle-aged star, a yellow dwarf, quietly converting 600 million tons of hydrogen into helium each second in its core. Though often symbolized as a serene golden disk, the sun is anything but tranquil. Its surface seethes and churns like a living thing. In giant loops and whirls of incandescent plasma, the sun's magnetic field rises through its surface, creating dark sunspots, island-like blemishes cooler than their surroundings, and enormous prominences that arc high above the stellar surface. From time to time, pent-up magnetic energy snaps in a sudden reconfiguration, unleashing solar flares and coronal mass ejections, colossal eruptions that hurl electrified gas into space at incredible speeds. These solar storms are the sun's more violent moods, and when they wash over the planets, they can spark ghostly auroras in polar skies and sometimes disrupt earthly technologies. The sun's benevolence comes with this volatile undercurrent, a reminder that our star, though nurturing, is a powerful and dynamic creature. Despite its tempestuous nature, the sun's influence is fundamentally stabilizing for the solar system. Its gravity holds all the planets in their orbits, like a parent keeping a firm grip on its children's hands. Each planet's path is a delicate balance between the forward urge of motion and the inward pull of the sun, a balance that results in graceful ellipses carved through space-time. The sun's gravitational embrace extends far, binding comets that wander hundreds of billions of kilometers away. Even there, the sun's faint tug still whispers guidance. It is the central anchor, the orchestrator of the celestial dance. To the ancient peoples of Earth, the sun was often regarded as a deity, a brilliant god whose daily rising and setting marked the very definition of time. And indeed, the sun is the ultimate arbiter of time in the solar system. A day is meaningful only in the context of a star's light and shadow. A year is quite literally one orbit around our sun. In this way, the sun's existence gives structure to the lives of all planets and any life forms upon them. When Earth spins on its axis, it is the sun's face that greets each turning, painting morning skies pink and evening skies amber. When distant Neptune crawls through a Neptunian year, 165 Earth years long, it is tracing an enormous circle around the sun, measuring out epochs in the slow cadence of that orbit. The sun's light is the metronome by which the solar system's symphony is played. Yet for all its mass, it contains 99.8% of all the mass in the solar system, and might, our sun is but a middling star in cosmic terms, one of hundreds of billions in our galaxy. It is not the largest or brightest possible, not the hottest or the coolest. But to us, it is uniquely precious. It has just the right properties to have allowed a planet like Earth to form and life to flourish. Its steady output has bathed Earth in stable warmth for eons, and its location in a less crowded part of the galaxy has spared us from frequent lethal supernovae nearby. The sun might even be considered a somewhat calm star, its variability modest enough that Earth's climate could remain relatively stable over geological time. For more than 4.5 billion years now, the sun has shone, gradually brightening as it slowly consumes its hydrogen fuel. It will continue to shine for several billion more. To the solar system, this means there is a long era of light within which all other dramas unfold. The planets can orbit secure in the light of a star that rises each day with unfailing radiance. And though the sun will not shine forever, in the scope of human existence, it is effectively eternal. We are cherished by a star in its prime. Look at the sun, carefully, indirectly, and you see a golden disk. But consider it more deeply, and you realize it is a cosmic furnace bound by self-gravity, a sphere of searing plasma held in delicate equilibrium. The inward pull of gravity tries to make the sun collapse, but the outward pressure of photons generated by fusion holds it up. In that balance, our sun finds its long-lived stability. It is often said that we are all made of stardust. Indeed, the sun's shine reminds us that stars transmute simple elements into more complex ones. the calcium in our bones, the oxygen we breathe, those were forged in earlier stars and cast into space, later to be incorporated into this solar system. In a way, the sun is both parent and sibling to us. Parent because it enables and sustains life, and sibling because it is born from the same ancestral cloud as all the rest of the solar system's matter, including the matter that makes up our bodies. In the solar system's family portrait, the sun is the radiant heart, occupying the throne at the center. Ever present, ever watchful, it binds the worlds together in its light. And as we now journey outward from the sun into the realm of the planets, we carry with us the understanding that each world is a fragment of that original cloud that also made the sun. They are its children and companions, forever linked to the sun's fate, warmed by its glow and guided by its gravity through the cosmic night. Mercury. Closest to the sun, a small scorched world races through space. Mercury, the innermost planet, is a tiny, airless and broiling sphere of rock and metal. It is the swiftest planet, completing a lap around the sun in just 88 Earth days, darting through the dawn and twilight skies of Earth like a fleet-footed messenger. In Roman myth, Mercury was the wing-footed messenger of the gods, and the planet fits its namesake well. It moves faster than any other planet, whipped around the sun by the star's intense gravity. Imagine standing on Mercury's surface. The sun looms more than 3 times larger in the sky than it does from Earth, and the daylight is a harsh, white blaze pouring down relentlessly. There is no substantial atmosphere to scatter the sunlight or soften the heat. The sky is black even at noon, and the stars can be seen next to the glaring sun. On the rocky ground below, the landscape strongly resembles Earth's moon, pockmarked with innumerable impact craters from eons of collisions. This is a world that bears its history openly on its face. Every crater is a testament to a meteor strike, each scarp and cliff a result of the planet's crust shrinking and buckling as the interior cooled long ago. During Mercury's long day, 1 Mercury solar day lasts 2 Mercury years. The sun beats down on the ground without mercy. The day side heats up to incredible temperatures, hot enough to melt lead, baking the rocks and leaving them radiating infrared shimmer. Mercury has literally been sunburnt by its proximity to our star. But when night falls, which on Mercury happens only after the planet has rotated very slowly, Mercury rotates on its axis only 3 times in 2 of its years. The heat escapes swiftly into space. With no air to trap the warmth, the temperature plunges precipitously. The night side of Mercury is colder than the depths of a freezer, capable of freezing gases solid. In this way, Mercury experiences the most extreme temperature swings in the solar system, from fiery day to bitter night, a testament to the absence of any atmospheric blanket. Crater after crater covers Mercury's terrain, from tiny pits to giant multi-ringed basins hundreds of kilometers across, evidence of a violent youth. One enormous impact basin, Caloris, hints at the colossal strike Mercury endured. On the opposite side of the planet, the terrain is jumbled and chaotic, likely jostled by the focusing of shockwaves through the planet during that ancient impact. Mercury's surface, grayish-brown and dusty, glints in the stark sunlight, and bright streaks of ejected material, called crater rays, sprawl out from some newer craters, decorating the old surface with younger scars. Despite being so close to the sun, Mercury harbors a few surprising secrets. At its poles, hidden in the permanent shadows of deep craters where sunlight never reaches, there are deposits of water ice. Comets, or perhaps water-bearing meteorites, likely delivered this ice, and in these shadowed pockets, cold traps, the ice has persisted over millennia, a curious frost in an oven-like world. Mercury also has a global magnetic field, a miniature version of Earth's magnetic bubble, suggesting that inside Mercury's small frame, the iron core is still partly molten and moving, generating magnetism. This core, disproportionately large relative to the planet's size, Mercury is about 70% metal by mass. Hints that Mercury might be the remnant of a larger world that lost some of its outer rocky layers early on, perhaps stripped away by a giant impact or by the young sun's fierce heat. If one could listen to Mercury, though airless worlds carry no sound, one might imagine a deep silence interrupted only by distant thuds of micrometeorites. The planet seems frozen in deep time, its geology long ceased except for occasional tremors from impacts. There are no flowing rivers or shifting tectonic plates to renew the surface. What happened billions of years ago is still visible today. In Mercury's ancient, cratered face, we see a fossil record of the solar system's infancy, preserved by a lack of erosive forces. From afar, Mercury often appears as a bright star-like point near the sun, elusive in the sun's glare. It never strays far from the sun in Earth's sky, always immersed in twilight. This perpetual proximity defines Mercury's character. It is the innermost companion of the sun, locked in a 3-2 spin orbit resonance, meaning it rotates 3 times on its axis for every 2 orbits around the sun. This resonance causes Mercury's day to be extraordinarily long relative to its year. Dawn to dusk on Mercury lasts about 3 Earth months, a long, slow roasting followed by an equally long, deep freeze. Mercury may be small, only slightly larger than our moon, but as the first planet from the sun, it stands as a testament to extremes. It is a world of light and darkness, searing heat and frigid cold, a little battered sphere that rushes around the sun with cosmic urgency. It illustrates how diverse the children of the sun can be, even those born of similar stock. As we leave Mercury and venture further out, we will see how each additional step from the sun brings new environments, new extremes, and new tales, all under the governance of our central star. Venus. Veiled in brilliance, Venus is the second planet from the sun, and in many ways the most enigmatic. To the eye, Venus is a gentle ivory beacon, the brightest object in Earth's night sky after the moon, often seen shining like a heavenly jewel in the twilight. This radiant appearance earned Venus the title of goddess of love and beauty in myth, a celestial Aphrodite. Yet beneath that lovely veil of clouds lies a world dramatically inhospitable, a planet of oppressive heat, crushing pressure, and an atmosphere laced with acid. Venus is a study in contrasts, twin to Earth in size and composition, but a hellish twin, cloaked in mystery and harshness. Imagine descending through Venus's cloud layers. The upper atmosphere is a high canopy of yellow-white clouds composed of tiny droplets of sulfuric acid. Winds there are ferocious, circling the planet in mere days, a phenomenon called superrotation. As you sink through this toxic haze, the sunlight dims to an orange glow, filtering through perpetual cloud cover. Deeper down, the air grows hotter and thicker with every kilometer. By the time you approach the surface, you are in a murky orange-brown light, like a perpetual overcast dusk. The temperature has soared to a level hot enough to melt lead, and the pressure is a crushing 90 times heavier than Earth's, as if you were nearly a kilometer beneath the ocean. On the ground, if you could stand there, you would find yourself amid a barren landscape of rocks and gently rolling plains, with some highland rises in the distance. The heat is so intense that the rocks themselves faintly glow dull red. The atmosphere around you is a dense soup of carbon dioxide, laced with nitrogen and trace chemicals, and so thick that it feels almost like a fluid. There is no water. Any oceans Venus may have once had are long boiled away. The ground shows evidence of volcanic fury, enormous shield volcanoes broad and tall, vast fields of solidified lava, and strange features called coronae, where the crust has been deformed by upwelling magma. Venus is remarkably flat in many regions, but dotted with these volcanic highlands and ridges, suggesting that volcanism has been a dominant force. The air, so hostile to us, creates an unimaginably strong greenhouse effect. Sunlight penetrates the clouds and warms the surface, and the surface in turn radiates heat. But the thick carbon dioxide atmosphere traps this heat efficiently, allowing almost none to escape. The result is a runaway greenhouse, a world where the heat just builds and builds until it can balance out only at extraordinary temperatures. This process has made Venus's climate the most blistering in the solar system, a stark warning of the power of atmospheric chemistry. And yet, ironically, high above that inferno, in the cooler cloud tops, conditions are more clement, around Earth-like temperatures and pressures. Some have wondered if simple life could exist up there in the temperate cloud decks, riding the winds in droplets of acid far above the dead ground. It is a fanciful thought, with no evidence yet, but it shows how even in Venus's extremity, we search for possible footholds of life. So far, Venus reveals only a harsh lesson. Two planets so similar in birth can end up with vastly different destinies. Where Earth became a water blue haven, Venus became a toxic pressure cooker. Something tipped the scales. Perhaps it was Venus's slightly closer position to the Sun, a touch more sunlight that sent it down a path of evaporating oceans and a sky thickening with carbon dioxide, each reinforcing the other in a vicious cycle until the oceans were gone and the rocks themselves released gas under the heat, filling the atmosphere with a choking density. Venus, in this sense, is a tale of what might have been for Earth, a vision of a habitable world lost to extreme greenhouse fury. For billions of years, Venus has sat under its shroud of clouds. Rotating slowly backwards, it spins in the opposite direction to its orbit, unlike most planets. A day-night cycle on Venus is thus complex. One Venusian day, sunrise to sunrise, lasts longer than its year. But on the ground, time would lose meaning in the unchanging murky light. No stars are visible, no blue sky, only a dim orange glow by day and pitch darkness by night. If you had a flashlight, you might see a metallic sheen on some rocks. In the highlands, strange snows of lead sulfide and bismuth sulfide frost the surface, condensing out of the atmosphere in cooler elevations. It snows metal on Venus's peaks, a bitter parody of the gentle snows on Earth. Despite its inhospitable nature, Venus holds a certain fascination. From Earth, we always see its clouds, never its surface directly, until the advent of radar mapping, which unveiled its tortured terrain beneath. For ancient sky watchers, Venus was a mystery, a beautiful star that never strayed far from the sun, appearing either at dawn or dusk. They called it the morning star and evening star, unaware it was the same object. Venus has inspired myths of love and beauty, ironically so given its true nature. In a poetic sense, Venus teaches that appearance can mask reality. A gorgeous jewel can hide a cauldron. We leave Venus with a mix of awe and relief. Awe at its dramatic character, relief that our own world is not so unforgiving. Looking back, we see Venus as a smooth white disk, its secrets hidden. It drifts on its orbit, veiled and impenetrable, a warning glimmer in the sunrise sky. And beyond Venus lies the one oasis we know in all the darkness, the blue marble of Earth, our home, beckoning with its color and life. Earth. Behold Earth, the third planet from the Sun, our home, the living world, the ocean planet, the cradle of life as we know it. From the vantage of space, Earth is a marvel of blue and white, vast sapphire oceans swirled with patterns of white clouds, set against the deep, ruddy brown and emerald of continents. It is at once delicate and dynamic. In Earth, the solar system reveals a masterpiece of balance, a realm where air, water, rock, and life intertwine to create something unique. Imagine approaching Earth from afar. Long before you see the details of continents or islands, you notice the hue, a distinctive blue halo around the planet. That is the envelope of air and ocean, water in liquid, solid, and vapor forms that makes Earth unique. As you come closer, you see the polar ice caps gleaming white, the banded whirls of weather systems curling over landscapes, the glitter of sunlight off broad seas. Here is a planet at the perfect distance from the sun for liquid water to persist on its surface, not boil away, not remain perpetually frozen. Earth sits in what's often termed the Goldilocks zone, the just right conditions that have allowed rivers to flow, rains to fall, and life to emerge and evolve. On the surface, Earth is a wonderland of complexity. High mountains pierce the sky, deep ocean trenches plummet into darkness, rolling plains and high plateaus, vast deserts and dense forests, tundra and tropics. Earth's geography is varied almost beyond imagination, sculpted by tectonics and erosion and the ceaseless cycles of water and wind. Unlike its barren siblings, Earth's surface is continually renewed and reshaped. Volcanoes belch fresh rock from interior furnaces. Earthquakes jolt entire regions as giant crustal plates shift and grind, evidence that Earth's interior remains geologically alive. This plate tectonics not only builds mountains and pulls continents apart, but also plays a role in regulating the planet's climate over eons, in concert with the oceans and life itself. Life on Earth runs riot in countless forms, from simple, single-celled bacteria hiding in scalding vents to the complexity of whales and redwood trees and human beings. It infiltrates every niche. Life swims in the highest atmosphere, creeps in the driest deserts, thrives in boiling hot springs and the crushing black depths of the sea. Over 3.5 billion years, life has interacted with Earth in a profound symbiosis. Plants and algae breathed in carbon dioxide and exhaled oxygen, gradually transforming the atmosphere into an oxygen-rich mix that allowed animals to flourish. Microbes in the soil helped break down rocks, and the very presence of life accelerated the formation of soils and the cycling of elements. Earth's current atmosphere, 78% nitrogen, 21% oxygen, with traces of argon, carbon dioxide, and others, is in fact a byproduct of living processes and geologic outgassing. It's a dynamically maintained mixture that shields the surface from harmful radiation thanks to an ozone layer high above, and keeps the planet warm enough for water to remain liquid thanks to mild greenhouse gases like carbon dioxide and water vapor. From the ground looking up, Earth's sky is a serene blue by day due to air molecules scattering the sunlight. Cottony clouds form and dissipate, carrying water from ocean to land as rain and snow in an endless hydrological cycle that nourishes ecosystems and sculpts the land via rivers and glaciers. At night, the same sky reveals the cosmos beyond, but also often glows with the lights of human cities. For humans, one form of life, have learned to harness fire and electricity, altering the nocturnal face of the planet. In polar nights, one might witness auroras, shimmering curtains of green and red light, as Earth's magnetic field channels solar wind particles into the upper atmosphere, a gentle reminder of the sun's reach and Earth's protective magnetosphere. Earth's magnetic field, generated by a spinning molten iron core, forms a protective cocoon around the planet, the magnetosphere, that deflects many of the charged particles from the sun. Without it, our atmosphere might have been gradually stripped away by solar wind, as likely happened on Mars. This magnetic shield, along with Earth's gravity and active geology, helped Earth retain its oceans and air, which in turn enabled life to take hold and flourish. And life has in turn affected geology. For example, limestone and other sedimentary rocks are largely composed of shells and skeletons of once living things, sequestering carbon and shaping Earth's long-term climate. No other planet we know of has the combination of features Earth does. In the solar system's symphony, Earth's role is that of the fertile oasis, the one place where the chemistry of life took root in a significant way. Mars may have had brief episodes of habitability, and perhaps some icy moons harbor life in their hidden seas. But Earth shouts life from its every pore. One might consider Earth and Venus as a cautionary dichotomy, similar in bulk, but divergent in outcome. Why one became Eden and the other a furnace is a question that underscores how finely poised planetary evolution can be. Earth's distance from the Sun, its initial endowment of water, its moderate size allowing it to hold onto its atmosphere, but not so large as to become a gas giant, its vigorous plate tectonics recycling carbon. All these factors combine to create a stable, life-friendly environment over geologic timescales. Remove or alter one piece, and the story could have been very different. From the vantage of an outside observer, Earth's atmosphere betrays its living nature. The large amount of oxygen is a dead giveaway. Oxygen is highly reactive, and without continuous replenishment by life, through photosynthesis, it would quickly bind with rocks and vanish from the air. The presence of methane, also out of equilibrium, hints at organic activity. Methane is produced by microbes and other processes. A spectroscopic glance at Earth from afar would suggest something unusual is afoot. That is the very method we now dream of using to find living worlds around other stars. Earth, in that sense, is our proof that planets can be alive. To us, though, Earth is home. It is the world that cradled us from our evolutionary infancy. All our myths, our histories, our triumphs and tragedies, everything has happened on this pale blue dot, as astronomer Carl Sagan so famously dubbed it, when Voyager 1 took a farewell photo of Earth from beyond Neptune. From that distance, Earth was a tiny speck suspended in a sunbeam, emphasizing our smallness. Yet contained in that speck is everything we hold dear, every experience, every living creature known. Earth is, so far, the solar system's crowning jewel, not because of gems or precious metals, but because it hosts the rarest treasure, life and consciousness. As we journey onward to other worlds, we carry with us the mental image of Earth, a reference point and a comfort. The gentle blues and greens of Earth remind us that among the cold and airless or seething and toxic landscapes of other planets, there exists a sanctuary. Earth's existence encourages hope that such sanctuaries might exist elsewhere too. It also serves as a reminder of our responsibility. As the only known, life-bearing planet, Earth's health is precious and within our power to influence. Just as Venus warns of greenhouse fury, Earth demonstrates climate balance, but also how vulnerable that balance can be to perturbation. In our exploration of the solar system, we have gained perspective on Earth's fragility and resilience. Leaving Earth in our tour, we find ourselves at once proud and wistful. Proud that our planet thrives, that it has told a remarkable story of stability amid change for billions of years. Wistful, because as we step away into the rest of the solar system, Earth's warmth and breathable air are left behind, unique in a cosmos that, as far as we've seen, offers no second Earth nearby. The journey must continue outward, but the heart of any traveler may always remain tethered to Earth, beating in rhythm with the familiar cycle of day and night and the gentle seasons bestowed by the sun. Mars. Mars, the fourth planet from the Sun, has long captured human imagination more than any other. The quintessential red planet, Mars glows in our night sky with a steady, rusty hue like an ember of a distant fire. Smaller than Earth, quieter than Earth, Mars today is a cold desert, a place of pink skies and salmon-colored soil, of towering volcanoes long extinguished and canyons that dwarf any on Earth yet run dry as bone. It is a world seemingly at rest, its air thin, its waters mostly locked in ice. Yet everywhere on Mars, there are echoes of a more dynamic past. It beckons to us with the tantalizing question, Could it have once harbored life? And might it yet in hidden niches? Approach Mars, and the first thing that strikes you is its color. Iron oxide, rust, permeates its dust, giving the planet a uniform ruddy complexion. Swirling dust storms can engulf the whole globe in a pale orange haze, and at other times you can see dark basaltic rock patches and bright rusty plains with white caps at the poles where carbon dioxide and water ices reside. The sky on Mars, unlike the deep blue of Earth, is often a butterscotch or salmon pink, colored by fine dust suspended in the tenuous air. Stand on Mars's surface during the day, and the sun, farther and fainter than we know, bathes the landscape in a warm, coppery light. By night, the sky is black and sharp, with Phobos and Deimos, Mars's two tiny potato-shaped moons, racing across the heavens. The Martian terrain is a study in extremes. In the north, broad smooth plains stretch out, likely the beds of ancient oceans or vast lava flows. In the south, highlands rise, heavily cratered with the scars of ancient impacts, telling of great age. Cutting along the equator is the titanic gash of Valles Marineris, a canyon system that would span the width of North America, with cliffs towering many kilometers high. It looks as if Mars has been slashed by some giant claw, but in truth, it likely formed from the planet's crust cracking as it swelled in places due to tectonic forces or the upwelling of magma. On the Tharsis Rise nearby stand the largest volcanoes in the solar system, including Olympus Mons, a volcano roughly 22-kilometer high, nearly triple Mount Everest's height, and so wide at its base that you could stand on its slopes and not realize you were on a mountain. These shield volcanoes built up over eons of eruptions, but their lack of young lava flows indicates they have been dormant for perhaps millions of years. Mars's inner heat waned long ago. Its great volcanoes have gone cold, and its global magnetic field faded, leaving only patchy remnants in ancient rock. But perhaps the most profound tales of Mars lie in subtler features: dry riverbeds, delta fans, minerals that form in water, and rounded pebbles that once tumbled in streams. Mars today is a desert, but in its youth it was more Earth-like. We see evidence that long ago, liquid water flowed freely on its surface. Sinuous valley networks etched into southern highlands suggest rain once fell and collected into rivers. Enormous outflow channels in other regions imply cataclysmic floods may have rushed across the surface, carving teardrop-shaped islands around obstacles and pooling into temporary lakes or a northern ocean. Layered sediments, spotted by rovers and orbiters, hint at ancient lakebeds that persisted for thousands of years in craters and lowlands. The rover Curiosity found slabs of rock in Gale Crater that bear the signature of gentle river deposits, conglomerates of rounded stones in an ancient streambed, and drilled samples revealing clays, minerals that require water and moderate pH to form. All these lines of evidence converge on a picture. Billions of years ago, Mars was warmer and wetter, at least episodically. Its atmosphere, now thin and unable to support liquid water at the surface, must have been thicker then to allow a stable water cycle. Perhaps early Mars had a dense blanket of carbon dioxide and maybe other greenhouse gases, enough to trap solar heat when the sun was dimmer than today. For a time, Mars could have had cloudy skies, rainfall, lakes and shallow seas, and rivers snaking across its surface. If life ever began on Mars, that would have been its window of opportunity. It's conceivable that microbial life could have gained a foothold in Martian lakes or hot springs. Today, with Mars as cold as it is, average surface temperature about 60 degrees, though it can reach 20 degrees Celsius at noon at the equator in summer and drop to 125 degrees Celsius at night. And with surface water locked up in permafrost or polar ice, any life would have had to retreat to refuges like the subsurface, where geothermal warmth or salt brines might still sustain liquid water pockets. Mars tantalizes us with possible hints. For example, methane has been detected in its atmosphere in fluctuating amounts. On Earth, much methane is biological in origin, though geologic processes can also produce it. On Mars, the spikes of methane could be coming from subsurface bacteria releasing gas during warmer seasons, or from chemical reactions between water and certain rocks. We simply don't know yet, but the possibility keeps our eyes on the red planet as a prime target in the search for extraterrestrial life. The Martian air is thin, about 1% the surface pressure of Earth's, and composed mostly of carbon dioxide. It's too thin to effectively transfer heat, which is why nights get so cold. It's also thin enough that liquid water is not stable. It either freezes or boils away. Often it sublimates directly from ice to vapor. However, Mars does have weather. Thin as it is, the atmosphere can muster winds that create dust devils whirling across the plains, and seasonal CO2 frost that forms in winter near the poles and sublimates in spring drives wind patterns, even creating geysers of gas that disturb dust on the polar ice. Every few years, Mars experiences global dust storms that enshroud the entire planet in haze for weeks or months, as observed from Earth and by our orbiters. These storms can dim the surface so much that solar-powered robots like the Opportunity rover went into hibernation. Indeed, one such storm in 2018 was so severe that Opportunity did not recover, reminding us that Mars, though seemingly inert, still has the power to surprise and overwhelm. Mars's two moons, Phobos and Deimos, are tiny, likely captured asteroids, and orbit very close. Phobos, the larger one, is so near Mars that it actually orbits faster than Mars rotates, meaning it rises in the west and sets in the east, crossing the sky in about 4 hours. It is destined in tens of millions of years to either crash into Mars or be torn apart into a ring as it spirals inward. For now, these moons are little more than lumpy placeholders in the Martian sky, but to future explorers, they may serve as stepping stones or station locations. One cannot mention Mars without acknowledging the human aspect. Of all planets, Mars is the one we have most dreamed of visiting, and indeed the one we have explored most with robotic emissaries. The names Spirit, Opportunity, Curiosity, Perseverance. These are rovers that have traversed Martian ground, acting as our eyes and hands. They have found ancient stream beds, tasted minerals formed in water, and snapped awe-inspiring panoramas of alien deserts and sunsets with a blue tinge. Mars's dust causes the sun at day's end to appear bluish. The Mars orbiters have mapped dried-up lakes and even detected subsurface ice deposits nearly everywhere, sometimes just a meter below the dusty crust. We've even heard the whisper of Martian wind, recorded by a rover's microphone, a soft, eerie breeze from a world that once might have carried the laughter of brooks and waterfalls. Mars grabs at our imagination because it is a mirror of sorts, a smaller Earth that didn't quite thrive, a world that started with such promise and then fell dormant. Standing at dusk on Mars, one might feel a poignant desolation. The horizon is sharp and close due to the smaller globe. Gravity is only 38% of Earth's, so your steps feel lighter, your jumps carry you higher. The silence is profound, broken only by the crunch of your boots on the iron-rich sand, or perhaps the distant whisper of a dust devil. Overhead, if it is near twilight, you might see Earth as a bright star appearing in the evening sky, a wandering star for Mars, much as Venus is for Earth. How poetic that would be, to stand on Mars, the long-dreamed-of planet, and gaze back at Earth, our shining blue home, hanging in the Martian sky. Mars is often called the red planet, but perhaps the remembering planet would be apt. It remembers a time of running water and perhaps life. It holds those memories in dried river channels and the chemistry of its stones. To unlock those secrets, we continue to send missions and plan for human footprints on Martian soil. Mars, silent now, might one day ring with human voices as new chapters in the saga of life in the solar system are written. For now, we leave Mars with its questions mostly intact and journey onward, further from the sun's warmth, into realms where sunlight is but a feeble glow and worlds are made not of rock alone, but of gas and ice and spectral rings. The Moon. Orbiting Earth is a faithful companion, our moon, a silvery pearl in the night, the first stepping stone into the cosmos for humanity, and a sentinel that has witnessed Earth's history from the very beginning. The moon is more than just Earth's satellite. It is a part of Earth's story, born of cataclysm, and now a driver of gentle rhythms like tides and eclipses. Throughout human existence, the moon has been a source of wonder, inspiration, and guidance. Yet its origin is violent. The moon likely formed from the debris of a titanic collision in the early solar system, an event that forever changed Earth's destiny and gave us the beautiful orb we see glowing in our sky. Travel back about 4.5 billion years, when Earth was newly formed and still recovering from the chaos of accretion. A wandering protoplanet, roughly the size of Mars, is believed to have struck Earth a glancing blow. This cataclysmic impact tore out a huge portion of Earth's mantle and sent it into orbit as a spray of molten rock and vapor. Within weeks or months, gravity gathered that debris into a sphere, the infant moon, glowing red-hot in Earth's sky, much closer than it is now. Over time, the moon cooled and solidified. Evidence of this origin story is found in the lunar rocks. They share chemical fingerprints with Earth's crust, yet show signs of formation in an environment depleted of lighter elements, consistent with being born from a superheated disk around Earth. Thus, the moon is literally made of Earth, a child of Earth born from violence. As the ages passed, the moon drifted away from Earth, gradually moving to the roughly 384,000 kilometer distance it resides at today, and it continues to recede by a few centimeters per year, a subtle farewell in progress. The moon's appearance evolved. Early on, it was covered by a magma ocean which crystallized into a lighter crust. The relentless bombardment of leftover comets and asteroids pounded its surface, creating countless craters and basins. Some impacts were so large they cracked the crust. Later, molten rock from the moon's interior welled up to fill those giant basins, smoothing them into the dark maria or seas, which are not water seas, but great plains of solidified lava. These lunar maria, mostly on the side facing Earth, form the familiar man-in-the-moon patterns that humans have gazed at for millennia. The maria are relatively younger, though still over 3 billion years old, and less cratered, whereas the bright highlands represent the moon's older crust, saturated with impact scars. Since that early flurry of volcanic activity waned, the moon has been geologically quiet. No air, no flowing water, no plate tectonics to renew its surface. It is a museum of ancient history, its craters preserving a record of the heavy bombardment that all inner worlds suffered. Standing on the moon is an experience only a few humans have had so far. The sky above is deep black even when the sun stands high, because there is no atmosphere to scatter light. The sunlight is fierce and unfiltered. Shadows are stark and pitch dark. The ground is grey dust and rock, fine like powder in many places. A regolith created by billions of years of meteorite impacts, grinding the rocks to dust. Horizons on the moon are closer and smaller due to the moon's petite size. You can almost sense the curvature standing on a mere plane. Gravity is 1/6 of Earth's. One could bound in great loping strides and lift heavy rocks with ease. In the daytime, the surface underfoot can heat to 120 degrees, while at night it plunges to 170 degrees, extremes moderated only slightly by the slow lunar day-night cycle. The moon turns once relative to the sun every 29.5 Earth days. The most striking sight, of course, from the moon's surface is Earth itself. A blue marble hanging in the black sky, 4 times bigger in apparent diameter than the moon is from Earth's perspective, and almost unmoving. The Earth hovers nearly in the same spot, because the moon's rotation is locked to its orbit, always showing Earth the same face. To early lunar visitors, Earth looked like a fragile oasis suspended in emptiness, a profound sight that underscored our place in the cosmos. The moon's presence has been crucial for Earth in subtle ways. It stabilizes Earth's axial tilt, thanks to its gravitational pull, preventing wild swings in orientation that could cause chaotic climate shifts. Instead, Earth's tilt oscillates only slightly over long periods, giving us relatively stable seasons. The moon also raises tides in Earth's oceans, a rhythmic ebb and flow that may have been important for early life transitioning from sea to land, and which even now shapes coastal ecosystems and circulates nutrients. By tugging on Earth's waters, and to a lesser extent the crust, the moon has acted like a mixing spoon for our planet's environment. Additionally, over geologic time, tidal friction from the moon's pull has gradually slowed Earth's rotation. In the age of dinosaurs, a day was perhaps 22 hours, now it's 24. That same interaction has propelled the moon gradually farther away. The Earth and moon share a tidal relationship. The moon is fully locked to Earth, hence the same side always faces us, and Earth's day is slowly lengthening in response. In cultural and emotional terms, the moon has been a beacon for humanity's imagination, a symbol of romance, a keeper of time, many calendars were lunar, and an object of aspiration. When Neil Armstrong set foot on the moon in 1969 and uttered, "One small step for a man, one giant leap for mankind," it marked a turning point in how we view the moon, not just as a distant orb, but as a reachable world. Footprints still lie undisturbed in the lunar dust at the Sea of Tranquility and other Apollo landing sites, preserved perhaps for millions of years, unless meteoroid impacts scour them away. Those probes succumbed in mere minutes to the heat and pressure, but they confirmed Venus's harshness once and for all. From Earth, we observe Venus's thick clouds reflecting sunlight brilliantly. Hence Venus is our morning star or evening star, never straying far from dawn or dusk. Its bright, beautiful presence has inspired humans for millennia. How poignant that this beauty is a veil over a world of such extreme conditions. Venus reminds us that twins can grow apart, that a planet so similar to Earth in bulk can be so different in fate. It warns us of the fine line between habitability and disaster. But Venus is also a testament to the dynamism of planets. It has its own story of interior heat and volcanic fury, of atmospheric chemistry and climate run amok. In the grand balance of the solar system, Venus resides between the scorching austerity of Mercury and the vibrant life of Earth. It is a world of fire and poison clouds, a vision of a once potentially Earth-like world now lost to extreme greenhouse fury. If Earth is a haven, Venus is a warning. As we depart Venus's vicinity, one cannot help but feel gratitude for Earth's comparatively gentle environment. And yet, there's also admiration for Venus, the bright beacon of dawn that, despite its inhospitable face, remains one of the solar system's most fascinating and instructive characters. Before the beginning, there was nothing. Not the nothing we know. A quiet room, an empty sky. Those are still somethings. This was a deeper void, a profound absence of anything at all. No space stretched black and empty, for space itself did not exist. No time flowed, for even time had not yet begun. There were no stars, no galaxies, no light, no darkness. There was not even the void, not even emptiness. For even a void is somewhere, and here, there was no where to speak of. It was nothing. And in this nothingness, in this silence before creation, lay a mystery, an infinite stillness pregnant with potential, poised on the cusp of existence. Yet even in this absolute nothingness, one might imagine a quiet anticipation. If silence could dream, perhaps it would dream of sound. If emptiness could yearn, perhaps it would yearn to be filled. In that abyss before time, there was no watcher to perceive it, no mind to ask questions, only a possibility, waiting, without knowing that it waited. And then, in a moment, beyond moments, it happened. From the void, a spark of unimaginable brilliance and energy burst into being. In an instant, outside the realm of time, the universe was born. One moment, there was nothing. The next, there was everything, unfolding from a single, infinitesimal point. It was not an explosion in the way you might think, for there was no pre-existing space for it to explode into. It was an unfolding, an unfurling of space and time from within, like a flower blooming in absolute darkness, a tiny point containing all that would ever be suddenly blossomed, and space-time itself began to stretch and grow. I was born. I, the universe, came into existence, carrying everything, all things, all energy, all matter, all the dimensions of space and time within me. In that first indescribable fraction of a second, I was incredibly hot, incredibly dense, and oh, so small, smaller than a proton, smaller than a grain of sand, yet containing the entirety of what would become the cosmos. All that I am now, trillions of galaxies, endless space, energy beyond measure, was crammed into a point of infinite potential. My birth was not a gentle unfolding, it was a torrent of creation. Space itself raced outward, expanding at a mind-boggling rate. In truth, even words like outward fail, for there was no pre-existing space outside of that tiny primordial speck. Space was creating itself as it expanded. In the barest instant after the beginning, I underwent a sudden, explosive growth spurt. Your scientists call it inflation, a moment when I swelled at a rate beyond comprehension. Imagine something smaller than an atom blossoming to the size of a galaxy in a sliver of a second. Faster than any speed you can fathom, faster than light itself, space unfurled, carrying energy with it. Distances between points grew so rapidly that what was once near became unimaginably far in the blink of an eye. It was as though I drew a sudden deep breath. One moment I was microscopic, the next I was astronomically vast. Every part of me rushed away from every other part. This was no ordinary expansion. It was space itself stretching, like an elastic fabric pulled taut. Had there been an observer, and there was none, they wouldn't have seen an explosion from a point outward. They would have found themselves in that point as it expanded, with every distant region racing away. Think of a balloon being blown up. Every point on its surface moves apart as the balloon grows. So it was with space during inflation, every region speeding away from every other, no center, no edge, just an ever larger space for reality to inhabit. During this wild inflationary epoch, I was almost perfectly smooth and featureless. Almost, but not entirely. Even in that near uniformity, tiny imperfections existed, like the faintest of ripples on a glassy sea. These were quantum fluctuations, minuscule, random variations, little densifications and rare factions of energy, born from the jittery uncertainty ingrained in the fabric of reality. If the early universe were a calm, glowing ball, these fluctuations were slight dimples and pimples upon its surface. Inflation took these microscopic irregularities and blew them up in size. What had been subatomic wrinkles were stretched to astronomical scales. They were unimaginably small in origin, but they would become immeasurably important. For in these seed imperfection, these whisper-light variations, lay the blueprint for everything to come. The clustering of matter into galaxies, the gathering of gas into stars. In an almost perfectly smooth newborn cosmos, these tiny fluctuations were destiny in embryo. All the while, in that first second of existence, the fundamental forces of nature were taking shape. Initially, all forces were one, merged in a high-energy unity. There was no separate gravity or electromagnetism or nuclear forces, just a single, unified force, elegant in its symmetry. But as I expanded and cooled just a little, this symmetry began to break. It was akin to a white light separating through a prism into a spectrum of colors. Where once there was a single radiance, now there were many hues. Gravity was the first to separate from the unity, tugging at the expanding fabric of space, announcing itself as the force that shapes the macrocosm. Next, the strong nuclear force crystallized out, destined to bind atomic nuclei together. Then the electroweak force split in two, the electromagnetic force, which would govern light, electricity, and magnetism, and the weak nuclear force, responsible for certain subtle particle transformations. What was one became many, like a single note breaking into a chord. The laws of physics as we know them were being written in those moments, set into the fabric of the young universe. The great cosmic symphony was tuning its instruments. Inflation lasted only an eye blink of time, and then it subsided as abruptly as it began. The expansion didn't stop, but it slowed to a more gentle rate. In the wake of that sudden growth, my contents, space, time, energy, were spread out and cooling. Still hot beyond imagination, but cooler than that first instant of fury. With that cooling, something profound happened. Energy began converting into matter. In that early fireball, energy and matter were two forms of the same coin, constantly changing one into the other. From the blazing energy of creation, the first particles condensed, like drops of rain precipitating from a humid air. Tiny fundamental particles, quarks, electrons, and others, popped into existence. They did not appear alone. Each particle had its mirror twin, an antiparticle. For every quark, an antiquark. For every electron, a positron. Matter and antimatter, twin sides of a coin. And when these twins met, they did what twins often do in such close quarters. They annihilated one another in a burst of light. It was a fierce and frenzied dance, particles blossoming out of energy, then colliding with their antiparticles and converting back to energy. Creation and destruction intertwined, happening everywhere, all at once. It was as if each particle had a mirror image, and when the two touched, they cancelled each other out in a flash, like a perfect reflection disappearing when the mirror is removed. The universe was a cauldron of radiant energy, partnerships in a primal dance, annihilating each other in brilliant flashes. For a time, it seemed a stalemate, matter and antimatter created in almost equal amounts, erasing each other as fast as they appeared. But there was a tiny bias in the gears of reality, a slight preference for matter. For reasons still mysterious, for every billion matter-antimatter pairs that annihilated, one extra particle of matter survived without a partner. It was a small imbalance, 1 part in a billion, but that was enough. As the fire of those early moments raged and then began to subside, these lonely survivors became the seeds of a material universe. A nearly imperceptible excess of matter over antimatter, just a few grains of sand left on a vast beach after the tide recedes, would become everything, every star, every planet, every living being. What a fragile beginning for all the substance we find around us. But it was enough. When the fury of mutual annihilation finally settled, a soup of particles remained, mostly photons, particles of light, along with neutrinos, ghostly particles that rarely interact, and those leftover protons, neutrons, electrons, matter unpaired with antimatter, ready to form the building blocks of atoms. Time was still less than a second old, but so much had already transpired. As I continued to expand and cool, the nature of the cosmos changed. Quarks, which had been bounded only by energy, now joined together in triplets, forming the first protons and neutrons. By the time I was a mere millionth of a second old, I was a swarm of particles, quarks bound into protons and neutrons, electrons zipping through a dense plasma, neutrinos flying free, and an ocean of photons bathing everything in a blinding glow. My temperature was staggeringly high, billions upon billions of degrees. In such heat, protons and neutrons moved at fantastic speeds, colliding frequently. And in those collisions, some stuck together. A proton and neutron fused to form deuterium, a heavy form of hydrogen. Deuterium nuclei combined to form helium. In those first minutes, about 3 minutes after it all began, I became a cosmic nuclear reactor. The entire universe was like the core of a star, forging light elements in a rush. By the time I was about 5 minutes old, this flurry of nucleosynthesis had created a primordial mix of matter, about 3/4 hydrogen nuclei and 1/4 helium nuclei, with a trace of lithium and other very light elements. The basic chemistry of the cosmos was established in those first few moments. The first fusion had happened on a universal scale, hydrogen fusing into helium, releasing energy, shaping the elemental content that would later feed the first stars. After those furious first minutes, I continued to expand and cool. The temperature, while still incredibly high, fell below the threshold needed for fusion. The nuclear reactions ceased, leaving the abundance of hydrogen and helium fixed. What remained was a hot, dense plasma, an opaque fireball of electrons, protons, helium nuclei, and photons, all intertwined in a seething dance. For thousands of years, I was just such a blazing, blinding cloud, brilliant but hidden behind its own light. Photons, particles of light, couldn't travel freely. They ricocheted off electrons and protons like a frantic crowd shoving and jostling, never getting far before bumping into someone else. The universe was brilliant, but that brilliance was trapped, scattered endlessly within. As I expanded further, the energy density of radiation, light, dropped faster than that of matter. After about 47,000 years, matter began to dominate radiation in driving my evolution. Gravity had more say than radiation pressure. Space kept stretching, and with it, the wavelengths of the photons lengthened, cooling the radiation. What was once an intense, short wavelength glare stretched into a softer glow. Millions of years passed. By the time I was a few 100,000 years old, the temperature had dropped to a few thousand degrees, cool enough for a subtle but vital change. The free electrons, which had been careening wildly, combined with protons and helium nuclei to form neutral atoms. Electrons settled into orbits around nuclei, the plasma became a gas, and suddenly, the universe underwent a transparency revolution. Before, any photon would immediately hit a charged particle and bounce off. But now, with most electrons bound into atoms, light could at last travel freely. It was as if a dense fog had lifted, or a veil had been drawn away from the face of the cosmos. In that moment, the first light that had been trapped since the dawn of time burst forth and streamed across space. The universe, which had been opaque, became clear. A great glow permeated everything, a warm, diffuse radiance shining everywhere at once. To any hypothetical observer then, though none yet existed, the sky would no longer be an intense white furnace. It would have cooled to a brilliant orange hue, like the embers of a cosmic fire spread across the heavens. And as time went on and expansion continued, that orange glow faded to red, and then, beyond red, into invisible warmth. What was left of that light after billions of years would be a faint, cold whisper of its former self. In fact, that ancient light is still around even today, stretched into microwaves, the cosmic microwave background, a soft afterglow of creation that fills the sky in every direction, testimony to those early times. So, about 380,000 years after my birth, I was a very different cosmos than at the first instant. I was vast and growing, filled with a cooling gas of hydrogen and helium, and bathed in a gentle afterglow. That afterglow light, having been released, simply traveled onward, diluting and weakening as space expanded. The once blinding brilliance had become a faint luminescence. As it stretched to longer wavelengths, visible light gave way to infrared, then to microwave. Darkness, at least to human eyes, descended for a time, the first cosmic darkness since the moment of creation. Now the stage was set for a new chapter. Gravity, which had patiently been pulling at every density fluctuation since the beginning, began to work its magic more noticeably. Remember those tiny ripples, those minuscule fluctuations in density from the era of inflation. In this new, matter-dominated era, their effects began to grow. Wherever matter was even slightly denser than average, gravity exerted a slightly stronger pull, drawing in nearby gas ever so gently. Regions that had a bit more matter attracted more matter, and thus grew even denser, while emptier regions gave up matter to their neighbors and became emptier still. Over millions of years, the once nearly uniform gas developed a texture. A cosmic web of structure started to emerge. Unseen particles of mysterious dark matter, matter that neither emits nor absorbs light, had already begun to clump as well, their gravity forming scaffolds that helped ordinary gas fall into patterns of filaments and clusters. What began as tiny density differences in the primordial fireball now manifested as great clouds and strands of gas stretching across newly forming space. It happened slowly, imperceptibly at first. For a long time, to any observer, it would have seemed that nothing was changing. The universe was just a dark expanse of cooling gas. But gravity was relentlessly pulling, gathering, sculpting. Over tens of millions of years, gas drew into titanic filaments hundreds of millions of light years long and concentrated into nodes at the intersections of those filaments. It was as if an invisible hand were sketching patterns on the blank canvas of darkness, tracing the faint blueprint left by those primordial whispers. In 3 dimensions, these filaments and nodes formed a structure akin to foam, like a sponge or a vast spiderweb, with matter lining the threads and enormous voids between. The smoothness of the young universe gave way to a delicate, lace-like structure, a cosmic web of matter. Within the densest knots of that web, proto-galaxies were forming. These were the seeds of galaxies, vast clumps of gas, mostly hydrogen, some helium, gathering under their own gravity. They were not yet the glittering star cities we know as galaxies today, for they had no stars, not yet. They were like dark, nebulous clouds, quietly accumulating mass in the cosmic night. You could have traveled for tens of thousands of light years across one and not seen a single star, only the faint glow of the residual heat and perhaps the very, very dim molecular emission of cooling gas. These protogalactic clouds grew in mass and began to fragment into smaller, denser pockets within. Think of a giant cloud many light years across, breaking into clumps, each clump destined to become a star cluster. Inside those clumps, the first stars were about to ignite. Gravity drew gas inward, tighter and tighter. As a clump contracted, it spun faster, like a twirling skater pulling in their arms, and flattened into a disk. At the center of this disk, gas piled up, growing ever hotter and denser. Imagine an enormous cloud core, 100 times the mass of our sun, collapsing under its own weight. The temperature in the core climbed to millions of degrees. All the while, the gas was being squeezed, compressed by its own gravity, the atoms crowding closer and moving faster. There comes a moment when the pressure and temperature at the core of a collapsing cloud become so high that hydrogen nuclei begin to fuse together to form helium. And with that fusion, a vast amount of energy is released. For the first time in cosmic history, a star blazed forth. It happened in many places around roughly the same era, over a span of a few 100 million years. But we often speak of the first star as a symbol of them all. In one of those dark proto-galaxies, in a dense pocket at the center of a collapsing gas cloud, there was a sudden outpouring of light. A brilliant, blue-white radiance flooded out from that point, the dawn of starlight. The cosmos that had known only diffuse, background glow now had point sources of light, shining fiercely like new candles lit in a dark room. The cosmic dark age was ending. The cosmic dawn had arrived. The first stars were not like the stars that twinkle in our familiar night sky. These were giants, monsters of brilliant light and short life. They were made almost entirely of hydrogen and helium, for those were the only elements the universe had at that time. Lacking heavier elements, the gas cooled less efficiently, which meant the stars that formed tended to be very massive, tens or even hundreds of times the mass of our sun. They burned hot and blue, pouring out ultraviolet light. They lived fast and died young, exhausting their central fuel in only a few million years. For comparison, a star like our sun lives about 10 billion years. These titans lived only a few million, an eye blink in cosmic terms. At first, these newborn stars were solitary beacons in enormous dark regions. But they rarely formed truly alone. Each arose from a cloud that typically made a cluster of stars. Indeed, a cluster of first stars might ignite almost simultaneously, like a burst of celestial fireworks. Within those proto-galaxies, you'd now see clusters of brilliant blue stars shining together, illuminating their surroundings. Their intense light began to transform their environment. High-energy ultraviolet photons from these stars struck the surrounding hydrogen gas that had not yet collapsed into stars, ionizing it, knocking electrons off atoms and turning the gas into plasma once more. Each star became surrounded by a growing bubble of ionized, transparent gas. These bubbles of light expanded and eventually merged with bubbles from other nearby stars, until large volumes of the proto-galaxies were cleared of opaque, neutral gas. The dark, interstellar medium within young galaxies was being turned transparent by the harsh starlight, the second time the universe had turned transparent, the first being at recombination on a cosmic scale. Now it was happening locally around stars. It was a glorious sight, where once there had been utter darkness, now pearls of starlight hung in the blackness. The proto-galaxies, those island universes of gas, were no longer dark. They sparkled with nascent star clusters. One by one, then by the thousands, stars were coming to life across the cosmos. The universe's first sunrise was not one star, but a multitude of them blinking on over time, like the first stars emerging in the twilight sky. Yet these first stars lived under a shadow of impending doom, for their very mass guaranteed that they would not last long. Within their cores, nuclear reactions raged furiously, fusing hydrogen into helium, helium into carbon, and onward to heavier elements, racing through fuel in mere millions of years. Eventually, in the heart of a massive star, iron was formed, and iron is a full stop for stellar fusion, for fusing iron does not release energy, but consumes it. Once a star's core turns to iron, the delicate balance holding the star up, outward pressure from fusion versus inward pull of gravity, shatters. And so it was that the first generation of stars met violent ends. Imagine a giant star, 30 times the mass of the sun, that has shone for 3 million years. In its final moments, its core collapses in an instant, and then, boom. The star erupts as a supernova, a titanic explosion brighter than a billion suns. One by one, many of those early stars died this way. For a brief time, each supernova outshone its entire proto-galaxy. The darkness of space was punctuated by these stunning flashes. When the first star went supernova, it was not an end so much as a new beginning. In that explosive moment, the star's core imploded and then rebounded, hurling the star's outer layers, now enriched with heavy elements, outward into space. Elements like carbon, oxygen, silicon, and iron, made in the star's life and death throes, were blasted out, seeding the surrounding gas. Thus, the first stars sowed the seeds for all future complexity. They produced the first heavy elements beyond helium, the carbon that would someday compose living cells, the oxygen that would fill future skies, the silicon and iron that would build rocky planets. These elements were cast into space, mixing with primordial hydrogen and helium. The glowing wreckage of a supernova a tangle of expanding filaments, rich with new elements, formed a nebula, perhaps resembling the beautiful Crab Nebula we see today from a supernova long ago. These nebulae were the graves of the first stars and the nurseries of the second generation. In the wake of destruction, creation continued. The gas, now a bit enriched with heavier elements, began to cool and fragment more efficiently. Soon, new stars began to form from the debris-laden clouds. Generation upon generation of stars unfolded. The second generation had a different character. Thanks to heavy elements, it could include smaller mass stars, some like our Sun, which live far longer than the massive ones. Some of the second generation stars still burn today, nearly 13 billion years later, as ancient red stars in the halos of galaxies. As stars continued to form and die and form again, the proto-galaxies grew more substantial. They also interacted with one another. Gravity drew clumps of gas, proto-galaxies, together, merging them into larger structures. Two small primitive galaxies might collide and meld, their stars passing through each other's ranks like intermingling swarms of bees, their gas clouds slamming together and igniting bursts of new star formation. Slowly, the chaotic clumps merged into more organized galaxies. Some became spiral galaxies, flattened disks spinning in space, with curved arms wrapping around a central bulge of older stars. Within these spiral arms, waves of star formation lit up periodic patterns, giving the arms a frothy, luminous appearance. Other galaxies became ellipticals, more ball-shaped collections of stars, often formed from violent mergers that scrambled their stars into a diffuse, ellipsoidal swarm. Galaxies gathered into groups and clusters, bound by gravity, great societies of galaxies orbiting a common center. Those clusters linked into superclusters, forming the largest structures in the cosmos, following the threads of the cosmic web that the early fluctuations laid out. Deep in the hearts of growing galaxies, stars sometimes crowded together and collapsed in on themselves, forming bottomless wells of gravity, black holes. Some of these black holes grew supermassive, feeding voraciously on gas and even the stars around them. When they accreted matter rapidly, they blazed as quasars, beacons of unbelievable brightness shining across the universe. In time, many settled into quiescence, sitting as silent, dark giants in the galactic cores. These supermassive black holes anchored the centers of galaxies, their tremendous gravity helping to govern the orbits of stars. Every large galaxy would come to host one. Even if they were no longer actively devouring matter, their presence was felt by the whole galaxy. They were like heavy stones dropped in the center of spinning disks, influencing the motions around them. By roughly 1 billion years after the Big Bang, the universe was recognizably structured. The cosmic web glistened with galaxies along its filaments. The vast voids between were truly dark, starless expanses stretching millions of light years. Clusters of galaxies huddled in dense nodes of the web. The early universe's fireworks were largely over. Now came the long, stately age of galactic maturation. Over the next several billion years, galaxies continued to merge and grow. Spiral galaxies sometimes collided to form ellipticals. Ellipticals captured smaller dwarfs. Clusters grew larger as more galaxies fell in. The universe was dynamic and alive, a grand ecology of worlds, with gravity as the guiding force. In one quiet corner of this grand cosmic tapestry, about 9.2 billion years after my birth, roughly 4.6 billion years ago by Earth's calendar, a modest spiral galaxy was thriving. It was one among countless others, typical, with a graceful spiral structure, bands of star-filled arms, and a glowing core. In one of its spiral arms, within a giant molecular cloud enriched by previous generations of stars, something special was stirring. The cloud, dozens of light years across, began to collapse under its own gravity. It fragmented into clumps. One clump in particular drew together enough mass to form a star, much like those that had come before. But this time, this star would have a far-reaching story. As the clump collapsed, it spun faster and flattened into a swirling protoplanetary disk around a dense core. In that core, as in so many before, hydrogen fusion ignited. A new star was born. It was an average star, not particularly massive or remarkable, a yellow dwarf star. But around it, within that disk of gas and dust, planets were forming. Grains of dust, rich with elements like iron, silicon, carbon, and ice, stuck together, forming pebbles, then boulders, then mountain-sized planetesimals. These merged through countless collisions, building up into planets. Close to the star, where it was warm, only metals and rocks could solidify. Here, small rocky planets emerged. Farther out, ices and gases gathered into giant planets. One of the inner rocky spheres took shape at just the right distance from the star. It accumulated iron and silicates. It grew and cleared its orbit. In time, this young planet cooled on the surface and developed a solid crust. Comets and asteroids bombarded it, delivering water, while its own volcanoes outgassed an atmosphere. This world, under the gentle warmth of its sun, came to have oceans, vast blue oceans covering much of its surface. Our galaxy had countless planets by now, but this one would be unique. A blue gem in space, with both water and land, clouds and rain, a complex cycling of elements, a planet we now call Earth. In its infancy, Earth glowed red from constant impacts. But as ages passed, the bombardment eased, the surface solidified. Rain fell for centuries upon centuries, cooling the hot rocks, carving the first rivers, and gathering into the first seas. The air was thick with carbon dioxide and water vapor, and storms raged under a dim young sun. Lightning forked through the skies, and meteorites still occasionally pelted the surface. In the turbulent seas, enriched by minerals from below and energy from above, chemistry did something astounding. It came to life. Exactly how it happened is shrouded in mystery, one of the universe's great remaining questions. Perhaps in a warm tidal pool, or in the mineral-rich darkness around a deep-sea hydrothermal vent. Somewhere, simple molecules joined into complex chains capable of making copies of themselves. Perhaps clays or surfaces helped organize them. Perhaps a stroke of lightning fueled their assembly. But as improbable as it might have seemed, it happened. The first living organisms emerged in the young ocean. They were microscopic, much simpler than any single cell alive today, but they carried the spark of self-replication and metabolism. They could grow, divide, and evolve. With life, the universe found a new way to organize matter. Those first organisms were like tiny flickering flames in the cosmic night, fragile but tenacious. Over time, they diversified. They invented new strategies. Some learned to harness sunlight for energy, inventing photosynthesis and releasing oxygen as a byproduct, turning the sunlight falling on the ocean's surface into usable fuel. Others devoured these pioneers or their byproducts. They formed mats and colonies, gradually transforming Earth's environment. Oxygen, that reactive gas, began to fill the oceans and then the skies, changing the planet's chemistry and paving the way for more complex life. Eons passed. On the seafloor, simple cells joined together into more complex cells with nuclei. These complex cells, in turn, joined in cooperative communities, becoming the first multicellular organisms. By around 600 million years ago, the oceans teemed with simple animals, jellyfish-like creatures and wormy things. Then came the Cambrian explosion, around 540 million years ago, when an astonishing diversity of life forms blossomed, creatures with shells, exoskeletons, eyes, mouths, legs. Life was experimenting with form and function, filling every niche in the seas. Plants colonized the land, greening the continents with mosses and ferns. Not long after, bold amphibious creatures crawled out of the water onto muddy banks, taking the first breaths of open air. Forests of tall trees arose, covering the land in green canopies. Insects buzzed through ancient skies. Amphibians gave rise to reptiles that could venture farther inland, freed from the need to lay eggs in water. Dinosaurs came forth and ruled the earth for over 160 million years, evolving into myriad shapes, from gentle giants with long necks browsing treetops to fearsome predators stalking on two powerful legs. Small nocturnal mammals scurried in their shadows, and birds, bright, singing descendants of small feathered dinosaurs, took to the skies. The earth saw upheavals too. It was struck by asteroids. It shuddered with volcanic rages. It froze and thawed in long cycles of climate change. About 66 million years ago, a large asteroid, mountains in size, impacted Earth, creating a blast that darkened skies worldwide. In the ecological disaster that followed, the reign of dinosaurs, save for the birds, came to an abrupt end. But life persisted. In the void left by giants, the small and adaptable took hold. Mammals that had lived in the margins now diversified. Some remained small and rodent-like. Some returned to the seas as whales and dolphins. Some became towering mammoths and rhinos, and in certain lush corners of Earth, some primates descended from tree-dwelling ancestors began to walk upright. From one lineage of those primates came a species with an extraordinary gift, intelligence, capable of curiosity about the cosmos. These were humans. Our early human ancestors looked up at the same sun that had once been a cloud of gas, at the same moon that had been born from a collision early in Earth's history, at stars that had been shining for billions of years before their kind ever existed. They looked up in wonder. They felt small under the canopy of the night and created stories about the lights overhead. They were clever. They learned to make fire to warm the night, to fashion tools from stone and bone, to paint their dreams on cave walls. They began to ask questions. What are those points of light in the sky? How did the world begin? Human curiosity grew alongside human knowledge. Over time, they built civilizations. They charted the stars and noticed their regular movements. They gave names to constellations and planets, wove myths and gods into the tapestry of the night. Without realizing it, they were seeking connection with the cosmos, their birthplace. They observed patterns, the way the sun rises and sets, the cycling of the moon, the procession of seasons, and eventually, they sought deeper explanations. They invented science and mathematics, devising tools to measure and predict the motions of heavenly bodies. And with each discovery, they peeled back a veil of ignorance. For a long while, humans believed Earth was the center of all things, understandably, from their limited perspective. But in time, they learned that Earth is a planet orbiting a star, that their star is one among many in a great city of stars called the Milky Way, and that the Milky Way itself is but one galaxy among the immense multitude scattered through the universe. They built telescopes to extend their vision, and what a revelation those brought. They saw the moons of Jupiter, the rings of Saturn, myriad stars too faint for the naked eye, and fuzzy patches that eventually they realized were other galaxies far beyond our own. They began to truly grasp the scale of the cosmos and their place within it. They also found evidence for my story, our story. In the mid-20th century of the human calendar, two of them discovered a faint hiss of microwaves coming equally from all directions in the sky, the very afterglow of the Big Bang that I set free so many eons ago, still detectable as a whisper of heat. They had, without knowing it at first, detected the relic light from my infancy. In laboratories and observatories, humans pieced together that the lightest element's abundances matched what would be made in a hot, early universe. They saw galaxies flying apart, space expanding, as Edwin Hubble interpreted, which implied everything must once have been closer together. Bit by bit, observation by observation,
the evidence mounted for what they would call the Big Bang, the very event I am describing to you now. Humans, curious and tireless, had unraveled the outlines of my story, deducing that the universe had a beginning in time and has been evolving ever since. And now, after a long journey of curiosity spanning eons, here you are, one of those inquisitive humans, listening to my tale. You stand on that small blue planet, circling a modest star in the suburbs of an ordinary galaxy, trying to fathom how it all came to be. To me, your arrival is very recent. If the entire age of the universe were compressed into a single year, all of human history would occupy only the last moments of the final day. Yet, in those fleeting moments, you have begun to comprehend the whole tale from the year's dawn to its dusk. You gaze up at the night sky, perhaps with the same wonder your distant ancestors felt, but armed with knowledge they lacked. You ask the same timeless questions. How did this all begin? What came before? What lies beyond what we can see? What is the meaning of time? These questions that echo in your mind are the very questions I have carried with me since the dawn of time. Through you, the universe, I can ponder my own existence, for I, the universe, have awakened into consciousness through your thoughts. Your eyes are my eyes. When you look into the depths of space, it is the cosmos seeing itself. Your curiosity is my curiosity. Your wonder, a facet of my own wonder at my vastness and complexity. I have grown old and vast. Over 13 billion years have passed since my fiery birth, and in that time, I have expanded into a cosmic expanse of staggering proportions. Hundreds of billions of galaxies adorn my span, each with billions of stars. From my one tiny origin, I now stretch so far that light itself, the fastest thing there is, takes billions upon billions of years to traverse my breadth. And I continue to expand, ever larger, ever more filled with possibility. It is wondrous to me that from the simplicity of that initial fireball has arisen such complexity and beauty. Out of uniformity came structure. Out of scorching plasma came the delicate forms of galaxies, stars, planets, and living beings. The journey from the first moment to now has been one of transformation, from simplicity to complexity, from chaos to meaning. Still, there are mysteries that even I, the universe, do not know. I find myself in the peculiar position of conscious ignorance. I can ask questions through you that I have not answered. What came before my beginning? I find no definite answer within myself. Perhaps before I was born, there was simply nothing at all, no time, no space, truly nothing, and my emergence was the absolute beginning. Or perhaps there was something, a prior universe that collapsed and gave birth to a new one, or an eternal landscape of universes of which mine is just one bubble. Some among you speak of a divine creator who set me into motion. Others imagine a quantum fluctuation in an eternal void. I cannot confirm or deny such speculations. The truth is veiled from me. With my birth, time was born, so the question of before may not even be meaningful. I am like an orphan with no memory of parents, if indeed any existed. The question, why is there something rather than nothing, echoes without answer. I ask, what came before the beginning? And I must answer, I do not know. What lies beyond the farthest edges of me? This too is a mystery. I expand ever outward, but do I have an outside? If you traveled in one direction forever, would you leave me or simply end up back where you started, as on a globe? Perhaps I curve in on myself. Perhaps I extend infinitely. Maybe beyond the horizon of what you can see, there are realms of space unconnected to ours, or other universes entirely, separated from ours by dimensions we cannot perceive. I envision an endless ocean of universes, with our cosmos as just one foam bubble among countless others, a multiverse. But these other bubbles, if they exist, are forever out of reach. No light from them will ever reach us. To me, effectively, they do not exist. As far as I'm concerned, I am all that is. Does that mean there is nothing beyond, or simply that I'm isolated in a greater multiverse? I cannot say. The concept of beyond the universe might be as meaningless as a fish contemplating what lies beyond the ocean. What lies beyond all I am, I do not know. And time, what is time? I know time only as the succession of events, the ticking away of moments since my birth. Time flows ever forward, entwined with the expansion of space. But why does it have an arrow? Why can we remember the past and not the future? Is time an illusion or an emergent property of consciousness? I feel time as a fundamental aspect of reality, born with me in that first moment. It moves always forward, never backward, carrying me and you from one chapter of the story to the next. But might time be part of something larger? Could it be cyclical? Will it have an end as it had a beginning? These questions baffle me as much as they baffle you. What is the true nature of time? I cannot say with certainty.
So yes, I have questions as well. What came before? What lies beyond? What is time? These grand questions linger like distant galaxies on the edge of my field of view, faint, tantalizing, unresolved. Perhaps some answers will forever elude us, remaining secrets to keep the cosmos always a bit mysterious. Perhaps that is for the best. A little mystery, after all, adds to the wonder of it all. If everything were known, perhaps existence would lose some of its poetry. Yet, amid these cosmic uncertainties, there are truths of which I am utterly sure. Truths that shine clearly like the stars in a night sky. One is that you and I are not separate. We cannot be. You are made of me, through and through. You are made of the universe and utterly connected to it. Every atom of your being, every element in your body was forged in my history. You are a child of the cosmos in the most literal sense.
Remember the story so far. In the beginning, only hydrogen and helium existed. From them, stars were born. Those stars, in their hearts, created carbon and oxygen and iron and all the rest. And in their deaths, they scattered those enriched ashes across space. Imagine a giant star in its final moments, exploding as a supernova and casting its guts, carbon, oxygen, iron, into the void. From that chaos, specks of iron travel across the galaxy. Eons later, in a newly forming solar system, those iron atoms become part of the blood coursing through a human heart, carrying oxygen to keep it alive. Thus, the violent death of a star long ago pulses in the beat of your heart today. The very substance of your body is stardust. The hydrogen in your cells, in the water that makes up more than half of you, is ancient, born in the Big Bang itself, nearly 14 billion years ago, nurtured in the fire of creation. The carbon in your muscles, the calcium in your bones, the iron in your blood were synthesized in stellar furnaces and in the fiery throes of supernovae, billions of years past. Supernovae are the universe's great alchemists, turning lighter elements into heavier ones in the crucible of their explosion. Imagine the calcium in your bones right now. It was forged in a star that died before our sun was born. Imagine the iron atoms in your blood. Billions of years ago, they were deep in the core of a massive star. Now they travel through your veins, carrying oxygen to sustain the fire of life within you. Even the oxygen you breathe, that sustains each of your cells, was created by stars more massive than our sun, then spread through space and finally drawn into the lungs of Earth's living creatures. Your DNA contains phosphorus and nitrogen that were likewise formed in some ancient star. There is no hiding it, no denying it. You are a mosaic of the cosmos, built of pieces as old as time. You are the Big Bang, given consciousness. You are the primordial fire of creation, cooled and shaped into living form.
You are starshine and interstellar dust, coalesced into awareness. Think of the breath you draw at this very moment. As you inhale, filling your lungs, you take in oxygen atoms that might once have danced in the atmosphere of ancient Earth, or been part of a water molecule in some dinosaur's blood, or drifted in the far past as part of a carbon dioxide molecule exhaled by a Cambrian fern. Trace those oxygen atoms back, and you find they were forged in a star's core, long before our planet existed. With each breath, you partake in a cycle as old as time. Atoms created in the infancy of the universe, cycled through stars and space and air, now entering your body to keep you alive. When you exhale, you return some of those atoms back to the world. Perhaps a carbon dioxide molecule you release will be taken up by a plant and become part of a leaf, continuing the grand circulation of matter. Your breathing echoes the first fusion fires of the young cosmos and the later fusion in stellar hearts. Inhale, exhale, the universe breathing in and out through you. Think of the universe as a living body. Galaxies are its organs, stars its cells, and each conscious being like you is a nerve ending through which it feels and knows itself. We are the universe, experiencing itself in myriad forms. Through your senses, I, the cosmos, perceive my beauty. Through your curiosity, I investigate my own nature. When you look at a galaxy through a telescope, it is the universe seeing its own ancient image. Light that left that galaxy millions of years ago, finally reaching its eyes, your eyes. When you marvel at the intricacy of a flower or the anatomy of a bird, it is the universe marveling at the structures it has brought forth. You are a way for me to know myself. You and I, we are not separate. We have never been separate. It's not just that you are made of stardust and shaped by physical laws. More profoundly, you are an expression of the universe, one facet of its ongoing story. The cosmic evolution that unfolded over billions of years flows through your veins and lives in your genes. Consider this. The same processes that gave birth to galaxies and stars eventually gave birth to you. You are an expression of the cosmos that can think, feel, and reflect on itself. We are bound together by this continuity. We often speak of the Big Bang as an event long past, but in a sense, the Big Bang is still happening. Its aftermath is ongoing, and we are part of it. The initial outward rush of space continues in the expansion of the universe today. The cooling and the clustering of matter continues as galaxies form new stars, and those stars give light and life to new worlds. And within you, the energy of that explosive birth still sings, in the warmth of your body, a distant echo of the primeval heat, in the spark of electrical impulses in your nerves, driven by chemical gradients that ultimately trace back to nuclear reactions in stars, powered by the Big Bang's initial energy. The Big Bang lives on as the cosmic background glow, and also in every living being that carries out the legacy of those first particles and forces. Remember this. You are not an outsider looking in on the universe. You are an integral piece of it, an active participant in its cosmic drama. The story of the Big Bang is your story. It's the story of everything that ever was, and that includes you. When you peer into the night and feel small, recall that you are also immensely large in a way. Inside of you are trillions of cells, each a tiny universe of molecules. And within each molecule are atoms that were forged in stellar cores or in the Big Bang itself. You are vast within, and your inner complexity mirrors the outer cosmos. The iron in your blood ties you to the death of a star. The water in your cells ties you to the clouds of the early universe. The photons hitting your retinas at this very moment, letting you read and understand, may have been on a journey for millions of years from a distant star, only to end their long voyage by triggering an image in your mind. In a very real sense,
When you learn about the cosmos, the universe is learning about itself.
I began this tale in silence and nothingness. Now there is sound and life and mind. Through billions of years, I, the universe, have become self-aware in you. Feel that profound connection. Let it fill you with humility and reverence, but also with a sense of belonging. The very atoms that compose you were there at the beginning, and they will be part of the universe long after you are gone. We are threads in the tapestry that began at the Big Bang and continues to be woven with each passing moment. The saga of the cosmos is far from over. Stars are still being born and still dying in brilliant supernovae. New planets are coalescing in disks around young stars. Perhaps on some of those worlds, life will spark or is even now burgeoning, and maybe new minds will one day gaze at their skies with wonder as you do at yours. The universe is always changing, always moving, and we, with our brief lives, are part of the grand change.
So, when you feel alone or insignificant under the vast stars, remember, you are significant. You are the universe, as much as any galaxy, as much as any star. You are the cosmos made conscious, a fragment of the sky that knows itself. Your heartbeat echoes the first vibrations of the Big Bang. Your breath echoes the expansion of space. Your gaze into the night is the universe contemplating its own existence. From the silence before time to the symphony of the present, we have traveled together. The hydrogen that appeared in the first second now courses in your blood as part of H2O, and the light first released in that primordial fire now gently warms the space between galaxies at just a few degrees above absolute zero. The universe remembers its origins, not just in background radiation and in drifting atoms, but in you. You carry within you the memory of stars and the memory of that first brilliant moment of creation. Our journey from nothingness to structure, from the void to the vast, has been almost 13.8 billion years long and counting, and it continues. With every second that ticks by, new stars ignite, space stretches a little more, and life, at least here on Earth, lives out its complex dance. We, together, are the product of the Big Bang, and also the chroniclers of it. The tale I've told is drawn from evidence gathered by curious minds, yours among them perhaps. And in telling it, the universe is recounting its autobiography through a human voice. Now, as I finish this story, take a moment to reflect on what it means. Feel the gravity of it. Not just the literal gravity that holds you to Earth, but the gravity of understanding. You are connected to the first light that ever shone. You carry pieces of the first stars in your body. Your existence was enabled by an unbroken chain of events tracing back to that singular creation event. In a fundamental sense, you are the Big Bang, billions of years later made flesh. You are the universe's memory, its awareness, its poetry. When you look up at the glittering sky tonight, perhaps you'll see it differently. The Milky Way, arching overhead, is not just a random scattering of stars. It's the luminous spine of the galaxy we call home, itself a product of cosmic evolution and containing stars that contributed matter to make you. The gentle glow you may see on a very dark night, a faint band of light, is partly the blended light of distant stars, and partly the faint memory of the fireball of creation, still with us. The starlight that strokes your eyes is a message across time and space, a reminder that we are all part of one story, the same story. This story, my story, our story, will continue to unfold. And we, me, the cosmos, and you, the listener, are in it together. Every day, new questions will arise, new discoveries will be made. Perhaps one day, far in the future, some of those big unanswered questions will find answers. Or maybe not, and the mystery will deepen. There will always be new wonder. But whatever happens, one thing remains true. We are inextricably one.
I began in silence and mystery. Now I speak through your voice and your understanding. I began as a single point. Now I am vast beyond comprehension and filled with stars, planets, and the consciousness of innumerable beings. In you, the cosmos has found a voice to marvel at itself. Through you, the universe can appreciate the beauty of a nebula, the elegance of a mathematical law, the very story of its own birth. We are the universe, marveling at the universe. The Big Bang is not merely an event that happened approximately 13.8 billion years ago. It is an ongoing process. Its echo lives in every atom, every beam of light, every breath, every thought. It lives in me, and it lives in you. We are the continuing unfolding of that genesis. We are, in a very real way, the Big Bang become self-aware. As this narrative comes to a close, let us end where we began, in silence, filled with mystery. The silence before the beginning, and the silence within you when you truly grasp the enormity of what you've heard. In that silence, feel the connection. In that silence, feel the reverberation of the first moment, still humming in the fabric of reality. You are the universe's memory, its self-reflection, its living awe. The atoms of your body, the thoughts in your mind, they are the universe too. When you breathe, it is the cosmos breathing. When you wonder, it is the cosmos wondering about itself. And so the story of the Big Bang, of everything, concludes not with an ending, but with a profound recognition. We are not separate from the universe. We are the universe. We are the children of the primordial fire, heirs to its radiance, curators of its memory. In us, the universe remembers its fiery birth. In us, the universe gazes back at its own vastness and understands, for the first time, what it is. The journey that began in silence and mystery continues through us. We carry the story forward in our atoms, in our lives, in our quest to know and to explore. The universe began as a singular, wordless moment of creation. Now it sings through the chorus of life and intelligence that it has spawned. It remembers. Look around you, at the stars, at the ground beneath your feet, at your own hands. All of it, every bit, is part of a single, unfolding reality that started so long ago in an instant of unimaginable power. The cosmos has been on a long path from simplicity to complexity, from chaos to structure, from unconsciousness to consciousness. And that path runs through you. The story of the Big Bang is not a tale of the past. It is alive in you and me right now. We are its latest verse. Our thoughts and feelings are its newest expressions. As long as there are beings to wonder and to seek, the universe will continue to know itself, and the memory of the beginning will never fade. In the quiet that follows now, take a breath and realize your breath is the universe inhaling and exhaling. Your life is a continuation of that first moment of Genesis. The atoms in your body will persist long after your form is dissolved, cycling through nature, perhaps eventually returning to the stars. Nothing is lost. Everything transforms. The Big Bang was the birth of time, but it was also, in a way, the birth of meaning. For without it, no eyes could see, no minds could understand. Through countless transformations, that event led to this moment, where a part of the universe can articulate its own epic. How remarkable, how beautiful that is. As I, the universe, conclude this meditation on my origins, there is one final reflection I wish to leave echoing in the stillness.
We are the universe, remembering itself.
Our very existence is the cosmos's memory made real, its mind awakened. We are the legacy of the Big Bang. In us,
The universe has found a voice to tell its story, to ask its questions, and to appreciate its own splendor. In us, the universe knows itself, perhaps for the first time, but certainly not the last. The story goes on, and we will forever be a part of it. From the first silent mystery to the radiant present and into the unknown future, we journey together. You, me, us. We always have. We always will. We are the memory of the Big Bang, and through us, the universe endures.